Okay, what's going on? Let's mic check. 1, 2, 3. 1, 2, 3. Okay, what's going on? Okay, we're good. Mic check. Notifications. Oh, parasocialism is one. Um, parasocialism.
I had the backer said that with this picture is parasocial and whatever. If you had given her something to control her and asking me to I had the backer sending me this picture and asking me to discuss. And I'm like, but why though?
Hello,
Is it
Lily.
because I'm a VTuber?
Hi.
Hey, what's up?
Nothing.
Hmm.
Yeah, I got class in a little bit.
Wait, are you in college or high school?
College.
Oh, well, you're a freshman, sophomore, senior? What are you?
Junior.
Junior. Then what's your major?
Political science.
Oh, nice. You should look into public choice theory.
Okay.
So, I have like revolutionary physics ideas. Did you hear about those?
Do you?
AU? What?
I said, did you?
Yeah,
Because I didn't know.
yeah, like something like really first class. Basically, I'm providing a foundation for special and general relativity. So I'm entering one layer below all of physics. I'm giving a support for the entire science of physics.
Wow.
Yes, it's really incredible. But a lot of people hate it. Like most people are really hating it. So, I'm being attacked. Like no one wants to
Mhm.
like no one wants to talk about it. Everybody's whenever I start discussing it, they attack me. They treat me like a flat earther basically. And and it doesn't matter how much I try to tell them I'm not a flat earther. I'm a vanilla physics person. I'm completely on board with mainstream physics. It's just that physics is lacking a foundation and I'm providing the foundation. But I'm not disagreeing with Einstein or any like mainstream physics. But it doesn't matter. They hate me and it's actually
Mhm.
it's very difficult. I'm having like very difficult days. Like my life has become very difficult.
Yeah,
Yeah.
got that.
Yeah. So wait, you're a political scientist. What do you think is going on the planet? It's like we're pre-World War III or something.
No. No.
So everything is
Like
fine.
we're at such a different level of like automation and technology than when World War I and World War II happened. There's just no way. Like that was fighting, I mean, on land for the most part, besides for obviously Hiroshima and Nagasaki. Like nobody's physically going to fight on land. Sure, you can say a World War III with drone strikes, which is gay, but nobody's attacking America and nobody's attacking China. I could hypothetically see someone attacking Russia. Ukraine already is, but which is just like a fucking proxy of like Americans attacking Russia if we're being real. But um nobody's attacking America, nobody's attacking China because that would just be stupid.
Right, but like, what if Israel escalates and the region starts going up in flames and Russia joins and then
Russia is so weak right now due to their war with Ukraine. So I wouldn't foresee them being a major player in that. Um, but even if Israel does escalate, the Saudis are not going to back this. And they are the ones with a lot of money in the region because Saudis literally banned Palestinians from entering their country. Like, Saudi Arabia really just want a part in this.
But what? I mean, Iran already. Oh, you left. Oh, what happened? Why did she go? Oh my God. Where is she? Wait, I didn't even send her an invite. What happened? Sorry, okay. Thanks for talking. Blah, 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 blah. So. Let me give you a link to my Discord. I'll give you a link to my Discord so you can Discord. So you can Discord to me. This is my Discord. Now let's get back to this guy. But I don't like, what is parasocialism? Like, is it socialism? I like when V, his name is V, when he discusses socialism because he grew up in socialism and he has a mechanical theory of socialism. Anyway, what I need to study right now, this is, I don't want to waste too much time. What I need to study, so I'm always getting stuck with the tensors. I don't know tensors, and these guys, I think they're assuming I know tensors. I don't know. I mean, he's mixing things that I've never seen before. I've never seen this. He says, oh, that's fine. Part for the course. I don't know what he's doing. I just don't know what he's doing. I just don't know. So I started looking into what is a tensor. So this tensor, right? So I heard that the word tensor comes from the word tense, tension. And this is, okay, that's good. So this tensor, this is good for the curvature of space-time, at least for the curvature of space. This defines curvature. This defines every force we can think of on a three-dimensional cube. So I know what this is. I mean, this is very foundational in engineering. I've used this before. This is like first year engineering. If you do mechanical engineering and stuff, this is first year. This is material, I think, material course, whatever you call it, strength of materials. This is like the first thing they teach you is this thing. It's really, it's amazing. So simple, so mechanical. Engineering is so simple. So, okay, I watched this video. This video made no sense. He, again, assumes I know a lot. I don't know. Okay, same goes for this. I watched this. He assumes I know a lot. I don't. Now, so shorts, I don't know if I want to watch shorts about tensors.
So there are certain misconceptions about tensors. Number one is that tensors are just fancy matrices. Absolutely not. Matrices can be up to a certain dimensions, but tensors can go up to any dimension.
This is interesting. So this goes back to what is a tensor. So this brings me back to where I came from. No, it doesn't. See, that's the problem with YouTube. The back button basically restarts everything. And I didn't see this before when we jumped forward. I think, okay, this video I saw before, but this again, this is a three-dimensional. This is the same as Asylum Academy, Asylum Science, whatever his name is, Nick. So I saw this video. I don't think it gave me any insight as to what it is. What's a tensor? I think, but he discusses a specific tensor.
Hi, I'm Dan Fleisch. When people hear that the subject of my new student's guide is vectors and tensors, a reasonably high percentage of them have the same question. What's a tensor? My goal for this video is to take about 12 minutes to answer that question, not using a bunch of mathematical equations, but instead some simple household objects, including children's blocks, small arrows, couple of pieces of cardboard, and a pointed stick. I think the very best route
That's good. So this is my philosophy. If you cannot explain it to a little baby, then you don't understand it. Okay, good start.
to understanding tensors is to begin by making sure
He has a very nice house. He has 2 candles here. I think he's Jewish. He might even be Orthodox. This is so a lot of you look at his name, Dan Fleisch. That's a very Jewish name. So this is like I'm getting a very strong vibe of Judaism. Let me see what I'm seeing. If I'm seeing here anything Jewish, there's nothing I recognize except for the 2 candles. Jews always have 2 candles for one of the rituals. And these look like used candles. These look like actual candles. What else do we see? Well, there's nothing Christian. And he's dressed very conservatively. This house, it's an old house. I get the vibe of New Jersey. This is like a New Jersey house. Nothing else screams. Oh, look at this table. This is a big table. This is a Jewish table. So he has a big family and guests, and they dine here. This is a big dining table. And they use it like people don't use dining tables so much, but he uses it. So that's pretty Jewish. Let me see. Okay, we have a message. I will after my shower. I miss my tub. Ugh. I'm waiting. Okay. So Dan Fleisch briefly explains. Wait. Dan Fleisch briefly explains some vector and tensor concepts from a student's guide to vectors and tensors. No way. 5,000 comments? How many views? 3.5 million views. And he has 50,000 subscribers. That is a huge channel. And this is electricity. So he's maybe an electric engineer. Let me see his channel for a second. Dan Fleisch. Nothing. No information. Just 20 videos. D Fleisch. Jesus. That's it. Just 20 videos. Student's Guide to College, Introduction, Student's Guide to College, Passion. So he's a professor. 5 years ago. You see, he aged since then. This is 12, right? Okay, 6, 7 years went by. 4 years ago. A Student's Guide to College, Review Sessions. Very interesting. A Student's Guide to College, Homework. Wow. Notes, math intensive classes, opportunities, class, expertise, integrity. Wow. Professors. Wow, this guy is awesome. Schedule. Oh my God, this guy is like, oh, look at all the books. Wow. Oh my God, this is so amazing. Oh my God, the eclipse. Roots of telecommunications, 3 minutes. 18 years ago, ancient Earth. 2 minutes. Oh my God. This guy doesn't need money. But by now, he's probably like really old. This is incredible. Wow. Amazing. So beautiful. It's really beautiful. And I don't know what this is, but all his videos are very short. They're always very short, never long form. Okay. Interesting guy. Okay, so let's listen.
That you're solid on your understanding of vectors. If you've taken any college level physics or engineering, you probably think of a vector as something like this: an arrow representing a quantity that has both magnitude and direction, wherein the length of the arrow is proportional to the magnitude of the quantity and the orientation.
But it's very interesting. A vector has magnitude and direction, but it doesn't have a location. That's really strange. Like a vector, if you really think about it, it's not, it doesn't have a location. It only has magnitude and direction, no location. That's really strange. So like, but the location is important. Why isn't there a located vector? Anyway.
Orientation of the arrow tells you the direction of the quantity. This could represent the force of gravity on an object, or the strength and direction of the Earth's magnetic field, or the velocity of a particle in a flowing fluid. But vectors can represent other things as well, such as an area. How does a vector represent?
So you could use two vectors. You could use one vector to locate an object and another vector to describe its velocity. These are These are two vectors. So one vector, right, and actually the velocity is the differential, or is the derivative of the first vector. So you can have one, right? So this is like very interesting. You can take the derivative of the first equation. So the first equation would describe a derivative. The first equation would describe a vector in time as a function of time and space, or it could give you, given time, a location would give you the like, let's say there's a function called location that gives you the location in XYZ if you input the time. So the equation converts t into a vector. So it outputs a vector if you input time. So given t, so location L is a function of t, but L is a vector. Let's say it's a 3D vector or 2D. So location could be a function given t. It converts t into some location, into an XYZ location. That's the output. So how would it has to output a vector. But that means it's basically three equations that have nothing to do with each other. One equation for x, one equation for y, one equation for z. How else would you describe a vector? I don't know. So you have three equations. Each one you input. Anyway, this is a whole universe of vector and vector calculus. Okay, so let's see what he says now.
Is that an area? It's pretty straightforward. You simply make the length of the vector proportional to the amount of the area, the number of square meters of the area. And then you make the direction of the arrow perpendicular to the surface. So in that way...
So you can use a vector to describe an area. You could use a vector to describe many things. Like, angular momentum, angular torque, or just torque. Yeah.
This can represent an area as well. So vectors can represent lots of things. But if you want to take the step beyond thinking of...
Oh, wait, I wanted to run my my cleaning robot. Where's my cleaning robot? It wanted me... Wait, couldn't update? Try again later? What? Wait. Let's try fully charged start. All right, it's gonna start. But wait, I need to get this thing out of the way. Otherwise, it's gonna hurt itself. All right. All right. Okay, so what is a tensor?
The vectors as representing quantities with magnitude and direction.
Let's see if our audio is still good. So your channel, this is our channel. So your channel, yeah, the audio is good. Very good audio. This is our channel. Very good audio. Very good. Very good audio. Absolutely very good audio. Right, all right. Let's get rid of this thing. Back to this.
To understanding that vectors are members of a wider class of objects called tensors, then you have...
It's like when you study something, you have to believe that it makes sense and that you can understand it. Right? If everybody agrees that tensors are a thing that makes sense and are useful, then it's just a matter of time before I'll figure it out. It might be difficult until I get it. Right now, I really don't have... I'm beginning to understand from the word tense, tension, tensor, and from some of the examples that I'm familiar with. I'm beginning to understand what a tensor is, but I want to get to a point where this makes sense to me, because right now I have no idea what he's trying to say here. All right, so let's continue.
have to make sure you understand vector components and basis vectors. If you're even going to think about the components of a vector, you better get yourself one.
So it just said components of a vector.
You have to make sure you understand vector components and basis vectors.
Vector components and basis vectors?
If you're even going to think about
components and basis vectors. I think basis vectors are like the XYZ. So there's I, J, K. Those are the basis vectors. So you have AI plus BJ plus CK, and that gives you, so A, B, C are the components, I guess, like the coefficients, and IJK are the basis vectors, which is the XYZ directions.
The components of a vector, you better get yourself one of these. This represents a coordinate system. In this case, I picked the simplest one, an x-axis, a y-axis, and a z.
This is basically like for water pipes, I think, no?
The axis, all meeting at right angles. This represents the Cartesian coordinate system.
Or maybe this is for electric components, for electric wiring. I don't know.
And the thing to remember about coordinate systems is...
So this is for the Cartesian. So this would be X, Y, Z. Let's see if this is... Does it obey the right-hand rule? I think so. If you go from X to Y, you get Z using the right-hand rule.
They come along with coordinate basis vectors. You probably ran into these as
that's an I, and he's going to place it along the X.
Unit vectors. And the thing
right, the unit vector, I think, is a basis.
Remember about these little guys is they have a length of 1.
Right.
One what? One of whatever the units.
Exactly, 1 unit.
That you're going to express the length of your vector in. And the direction of the basis vectors or unit vectors is in the direction of the coordinate axes. So this might represent the unit vector in the x direction. That's often called x with a little hat over it, or sometimes I hat. That's the x hat unit vector. It points in the direction of increasing x coordinate. Likewise, the y hat, sometimes called the j hat unit vector, points in the direction of increasing y. And the z hat or k hat unit vector points in the direction of increasing z. Once you have the coordinate system and the unit vectors in place, now you're in a position to find the components of your vector. But how exactly do you do that? I think it's easiest to understand how to find vector components if you begin with a vector in the xy plane. So I'm going to lay this vector in the xy plane at some angle to the x-axis. In order to find...
So he got rid of the z dimension. So he's only going to do this in the xy dimension. 2 dimensions.
The x component, I'm going to project this vector onto the x-axis. In order to find the y component, I'm going to project this vector onto the y-axis. And how am I going to do those projections? Here's one way. I've darkened the room because I'm going to use this lamp to project the vector onto the x and y axes. First, I'm going to shine the light perpendicular to the x-axis, that is parallel to the y-axis, and look for the shadow of the vector on the x-axis.
This is genius.
That will be the x component of this vector. As you can see, the shadow of the vector on the x-axis ends right here. This is the x component of this.
This is genius.
Vector. If I made the vector have a greater angle to the x-axis, notice the shadow moves this way. The x component is getting smaller. And if I make the vector lay entirely along the x-axis, then the shadow and the vector are the same length. The x component is the length of the vector.
Well, it's difficult to tell, but yeah, I understand.
In that case. Now I've got my light shining perpendicular to the y-axis, that is parallel to the x-axis, and the shadow cast by the vector onto the y-axis.
Well, you should have shown us. You shouldn't do cuts. Cuts are terrible. You should show the whole thing slowly. You should show us where you place the lamp, because we can't see it.
Gives me the y component of the vector. Notice that as I increase the angle to the x-axis, I'm decreasing the angle to the y-axis, and the y component is getting bigger. Another way of visualizing vector components is to ask yourself, to get from the base of the vector to the tip of the vector, how far do I have to go in the x direction, and how far do I have to go in the y direction?
Yeah, but he's explaining vectors. Why is he spending so much time on vectors?
In other words, how many x hat or I hat unit vectors?
It's like people are teaching something, and then at the end, last word, and that's a tensor. Wait, what? Wait, and then they do some crazy math, really advanced. What? What are you talking about? You didn't teach this.
Vectors, and how many y hat or j hat unit vectors would it take to get from the base to the tip of this vector? I can show you this if I get rid of these axes and just line up some x hat basis vectors. These are going to go in the x direction, obviously. And some y hat basis vectors.
Well, you should be able to connect them, and then it's easier. They wouldn't roll as much.
So in other words, this vector is made up of about 4 x hat and 3 y hat. That means that instead of drawing an arrow for this vector, you could simply say 4 of these plus 3 of these. And if you want to be complete, since there's no z component to this vector.
So the components are the block. These are just the coefficients.
0 of these. That is the same as this. In other words, this is a perfectly valid representation of that vector. And of course, if you know the basis vectors, you wouldn't even have to put these on, would you? You could simply use these components as your vector. You could write them in a little array. You could even stack them up. Put a nice set of parentheses around them. This looks just like the way you see column vectors written. Of course, these 3 components pertain only to the vector we had laying on the table a minute ago. To generalize this, the vector capital A, for example, we can replace these components with a sub x, a sub y, and a sub z. Of course, a sub x is the component that pertains to the x hat basis vector. A sub y pertains to the y hat basis vector. A sub z pertains to the z hat basis vector. Notice that we need one index for each of these because there's only one directional indicator, that is one basis vector, per component. This is what makes vectors tensors of rank 1. One index.
Okay, so vectors are tensors of rank 1 because...
One basis vector per component.
What?
By the same token, scalars can be considered to be tensors of rank 0 because
Spheroids? What?
scalars have no directional.
Scalars. Scalars are 0 because they have no directional. I don't understand. So this one, each component has one direction. So it's scale rank 1.
No indicators, therefore, need no indices. Those are tensors of rank 0. I'll say in a minute why it's so powerful to represent tensors as this combination of components and basis vectors. But first, I want to show you some examples of higher rank
Components and basis vectors. That's just a vector.
tensors. This is a representation of a rank 2 tensor in 3-dimensional space. Notice that instead of having 3 components and 3 basis vectors, we now have 9 components and 9 sets of 2 basis vectors. Notice also
This is... I've never seen anything like this. This is a plane. Another plane. I don't know what this is. This is a plane. I don't know what this is. Another plane. Same as this. I don't know. What the heck is going on? What is this?
also that the components no longer have a single index, they have 2 indices. Why might you need such a representation? Consider, for example, the forces inside a solid object. Inside that object, you can imagine surfaces whose area vectors point in the x, or in the y, or in the z direction. And on each of those types of surface, there might be a force that has a component in the x, or in the y, or in the z direction.
Oh.
So to fully characterize,
So what he means to say here is that this represents the surface. This is the surface. So one of them is the surface, the one that points to the right. Then you see that all of these have a forward facing one. So this is the right side of a cube. This is, let's say, the far side of a cube. And these are all the top side of a cube. So the right side, the far side, and the top side. Anyway, and for each one, so this is the right side of the cube, a shear force up, shear force away, and a tension. And here you have a far side of the cube, shear force up, tension. Right, so this is far side, shear, tension. Again, no, it's not. Oh, sorry, we're here. This is the far side. So the far, and this is shear to the right. This is the top side of the cube. Top side, this is tension. Top side, shear away. Top side, shear to the right. Okay, it's very partial. And this is a very partial. So this is a rank 2 because you need 2 indices for each component has 2 indices. Okay.
Characterize all the possible forces on all the possible surfaces, you need 9 components, each with 2 indices referring to 2 basis vectors.
So this is rank 2 something, I don't know. This is a 3 by 3. I don't know. But rank is 2, but there's rank in something else.
For example, a sub xx might refer to the x-directed force on a surface whose area vector is in the x direction. A sub yx might refer to the x-directed force on a surface whose area vector is in the y direction, and so forth. This combination of 9 components.
That doesn't. Well, so this could represent what I said, but it could represent something else. Okay.
And 9 sets of 2 basis vectors makes this a rank 2 tensor. This is a representation of a rank 3 tensor in 3-dimensional space. 27 components, each pertaining to one of 27 sets of 3 basis vectors. I'll zoom in a little bit here so you can see.
So it's 27 because it's 3 to the power of 3. Is it? I think it's 6 times. There's 6 sides to a cube, right? There's 4 and 2 more, so it's 6. And each one, so each side, yeah, I don't know why you have 27. What are you trying to represent? Like an engineering tensor, a material strength tensor doesn't need so many. There's only 3 per side and 6, so it's only 18 components. This is 27. What are you going to describe with so many components?
The components better. Notice that now each component has 3 indices. A sub xxx pertains to 3 x basis vectors. A sub xyx pertains to 2x and 1 y basis vector, and so forth. This entire front slab has x as the 3rd index and pertains to these 9 sets of basis vectors. The middle slab all has y as the 3rd index and pertains to these 9, and the back slab all has z as the 3rd index and pertains to those 9. So in 3-dimensional space, 27 components, 27 sets of 3 basis vectors, and 3 indices on each component. You may be wondering.
This is so confusing. I don't know what the heck is going on. What is the power of tensor? What are they used for? That's where you should start from.
What is it about the combination of components and basis vectors that makes tensors so powerful? The answer is this. All observers in all reference frames agree, not on the basis vectors, not on the components, but on the combination of components and basis vectors. The reason for that is that the basis vectors transform one way between reference frames, and the components transform in just such a way so as to keep the combination of components and basis vectors the same for all observers. It was this characteristic of tensors that caused Lillian Lieber to call tensors the facts of the universe. Thanks very much for your time.
Okay, that's terrible.
The facts of the universe. Thanks very much for your time.
D. Fleisch at Wittenberg Edu. Alright, so he's a professor. What is Wittenberg? He teaches at a place called Wittenberg. Never heard of Wittenberg. So he's not in New Jersey. There's no Wittenberg. I don't know where he is. Tensors for beginners.
All right, welcome to this video series on tensors. In this first introductory video, I'm going to try and give you a bit of motivation for why you might want to study tensors, and then in later videos, I'll get to explaining what tensors actually are.
Yeah, motivation comes before. Oh my god, this is all tensors. This is tensors for beginners? Oh my god. All this is tensors for beginners? There's like an hour here. 18 times about, on average, I would say 10 minutes. That's 180. That's 2 hours of math. Oh my god.
So before I start, I should mention that I expect people watching this video series to have a little bit of linear algebra under their belts already. So I'm hoping you already know how to multiply matrices and you know what terms like linear combination and dot product are. If you don't know any of this stuff, you're welcome to watch anyway, but you might find it a bit harder to keep up. What I'm going to try to avoid doing is doing any mention of calculus. Some people like to introduce tensors using calculus, but you really don't need that. You only need linear algebra. I'm going to talk a little bit about calculus and tensors at the end of the video series for people who do have a calculus background, but I'm going to do my best to avoid any mention of them until then. All right, so why should we want to study tensors? So the main reason you would want to study tensors is geometry. If you understand tensors, then you can get a lot of insight into how geometry works. Now, I'm not talking about the geometry you would have learned in elementary school or high school, stuff like basic shapes or trigonometry. I'm talking about geometry that can be fairly complicated and not very intuitive. So one example of such geometry is the geometry of space-time in Einstein's general relativity. So let's talk about that a little bit. So if you've ever read or watched any popular science articles or videos on general relativity, you've probably heard about how space-time is curved and how light can travel in a curved path around massive bodies like stars and black holes. Another thing you might have heard about is how the universe is expanding, right? So at the beginning of time, we had the Big Bang here, and ever since then, the universe has been getting bigger and bigger, and so the universe is expanding. Now, when you first hear these ideas, you're probably thinking, what the heck do these even mean? What does it mean for space-time to be curved? What does it mean for the universe to be expanding? So in order to understand these ideas mathematically, we need tensors. So I'm just going to throw up some equations on the board right now. So these are Einstein's field equations. And I say equations with an S on purpose because even though it doesn't look like it, there are actually 16 equations here. And these 16 equations tell us how space-time is curved and why the universe is expanding. Now, you don't need to understand what any of these symbols mean, but the important thing that I'm going to point out to you is that every symbol that I'm underlining right now is actually a tensor. So there are tensors everywhere in these equations. And the most important tensor in general relativity is this one here, the G, which is called the metric tensor. It's a 4x4 rank 2 tensor, which you could also call a 4x4 matrix, and it helps us measure lengths and angles in the curved geometry of space-time. Now, I'm going to talk about the metric tensor in, I think, video 7 or 8. I'm going to use much simpler examples than the ones you'd see in general relativity, but hopefully you'll understand what the metric tensor is, and you'll take in the first few steps toward understanding why space-time is curved and why the universe is expanding. All right, so another example of tensors being important is in quantum mechanics, and in particular, quantum computing. So,
Really? You're going to explain why the universe is expanding? Wow.
quantum computing is a pretty active field of research these days. If we ever get quantum computers working, they'll be able to solve some problems that the classical computers we use today are not able to solve, or at least the classical computers we have today can't solve them very efficiently. Anyway, again, if you've ever seen popular science articles or videos on quantum mechanics, you've probably heard the term quantum superposition. And so this is the idea that quantum systems can be in two states at once. And usually they give some weird
They can't.
example involving a cat being dead and alive at the same time. I'm not sure how literally you want to take that, but there it is.
So don't say it if it's not literal.
And so another idea in quantum mechanics is the idea of quantum entanglement. And so this is the idea that two particles can become entangled, and even if you separate them by hundreds of kilometers, they can still influence each other in strange ways
No, they can't.
because they're connected using this strange quantum
There's nothing strange. There's nothing strange in this universe. This universe is straightforward.
entanglement property. So again, what do these terms even mean? What's quantum superposition and what's quantum entanglement? What do these mean mathematically? So it turns out that superposition, if you know a little bit of linear algebra, superposition is just a fancy way of saying linear combination. So with linear combinations, what we do is we have what you might think of as simpler vectors, and we combine them together using scaling constants and addition to get a more complicated vector here. And it turns out in quantum mechanics, physical quantum states are actually just vectors. And so we can combine simpler states together using linear combinations to give us more complicated states. And so that's really all quantum superposition is. As for entanglement, when two quantum systems are entangled together, what we really mean is that these state vectors have been combined together using something called the tensor product. And that's what this circle X symbol is. It's the tensor product. So what the tensor product does is it takes the geometrical space where the first system lives and the geometrical space where the second system lives and combines them together to create a more complicated geometrical space. And that's where the entangled system lives. So I'll be talking about the tensor product in, I think, video 9 or 10. And hopefully that will be a first step toward understanding quantum entanglement mathematically. All right, so hopefully I've made you at least a little bit curious, and hopefully you want to learn a little bit more about what tensors are. In the next video, I'm going to start explaining.
That's a terrible motivation. It's not motivation. That's the most wrong motivation. You need to show how you use them. Show me how you use tensors. That's motivation.
What tensors actually are.
Give me a problem that I should be able to understand, but I should not be able to solve, and show me how you can solve it. And basically the only way to solve it is using a tensor. That should give me motivation, and already I'll see you using them, and I'll begin to get intuition as to what they are. People don't know how to teach, unfortunately.
And after that, we can get started learning some actual math. So I'll see you in the next video. All right, so welcome to this second video in my series on tensors. In the last video, I tried to give you a few reasons for why you might want to learn about tensors. In this video, I'm going to try and explain what exactly tensors are. So tensors are a little hard to describe if you've never heard of them before. So what I'm going to do is I'm going to give you several different definitions that you might hear from
No, don't start from definitions. Start from the usage.
different people when you ask them what a tensor is. And hopefully seeing all these different points of view will put you in a good starting position so that you feel comfortable when we actually start doing real math in the next video. Okay, so let's get started. Here's a first attempt at a definition for tensors. I'll just read it off. So a tensor is a multi-dimensional array of numbers. And by array, I basically just mean grid. So a grid of numbers. Okay, so let's see some examples of what this might look like. So the simplest example of a tensor is what we would call a scalar, or sometimes a rank 0 tensor. And a scalar is basically just a number. So any number like 1, 2, 5, 3/4, pi, these are all examples of scalars. And we don't normally write scalars as arrays, but if we wanted to, we could write little square brackets around the scalar like this and sort of pretend it's an array, but we don't normally do that. All right, so those are scalars. Another example of a tensor you've hopefully seen before is a vector, or a rank 1 tensor. And we call it a rank 1 tensor because it's a list of numbers that extends downward in one dimension. So it's like a one-dimensional array. So that's a vector. Another example you've probably heard of are matrices, or rank 2 tensors. And we call them rank 2 because they are a two-dimensional grid of numbers. So they extend up, down, left, right. And if you recall from the last video, I mentioned that the metric tensor from general relativity is a rank 2 tensor. And these little Greek letters that you see here actually stand for numbers that represent the row and column of the particular entry of the matrix that we're talking about. So the metric tensor is really just a matrix. And we can go higher and higher. This is a rank 3 tensor because it's in a three-dimensional grid of numbers sort of arranged in a cube. And we can go on and on, rank 4, 5, 6, as high as we want.
Okay, so rank 3. Okay, I don't know, like... this is a vector in n space. And this is a matrix in n space, n n. So it's a square matrix. I don't know what these subscripts are. So rank 2 just means there's 2 subscripts, and rank 3 just means there's 3 subscripts. So rank 3 tensor doesn't have another name. I mean, it's just okay.
So any multidimensional array of numbers is a tensor. So I call this the array definition of tensors. Okay, so I said that this was a first attempt at a definition, and it does give us some idea of what a tensor is, but this definition is actually wrong, and here's why. So tensors can be represented as multidimensional arrays, but that's not what they fundamentally are. Tensors aren't just a bunch of numbers that we toss together. Tensors actually have real geometrical meaning, and if we just think of tensors as these multidimensional arrays, we sort of miss out on the geometrical meaning behind them. So if we casually toss the word tensor around to mean a multidimensional array of numbers, that's sort of fine. There's nothing wrong with that. But if we're thinking seriously like mathematicians and we want to understand geometry, this...
Let me check the geometry of my robot. Let me see how it's doing. So every time it drives around the house, it rediscovers the house. It's doing a rediscovery. What just happened? Water level? Standard, medium, turbo. Vacuum and mop. Duration 23 minutes. Battery 93, area 25. Okay. Nice.
Definition, the array definition is simply just wrong, so it's no good to us. Okay, so let's try again. So here's another tentative definition. I'll just read it. A tensor is an object that is invariant under a change of coordinates and has components that change in a special predictable way under a change of coordinates. Okay, so that's certainly a mouthful. So what does that mean? So let's start with the top part. What does it...
Right, so this is the beginning of the invariance. This is the truth. This is what we're looking for. We're looking for something true about the universe. We want to say something that is true about the universe that is invariant to any coordinate system. It's true in all coordinate systems.
What does it mean to be invariant under a change of coordinates? Well, to explain that, I'd like you to try picking up a pencil and point the pencil toward the nearest door that you can see. So there are a few things that we can say about this pencil that are just facts, and they don't depend on any coordinate system. So for example, the length of the pencil, the length won't depend on our choice of coordinate system. The length is an intrinsic or invariant quantity. Also, this pencil is pointing toward the door, and that's just a fact. It doesn't depend on what coordinate system we use. The pencil's orientation is intrinsic or invariant under the choice of coordinate system. Now, the second part, what does it mean for components to transform predictably under a change of coordinates? Well, to start off, let's introduce a coordinate system here. So we have a nice 3D coordinate system with 3 vectors.
Basically, it doesn't matter from where you look at the pencil and the door. The pencil is pointing at the door. From anywhere you look at the pencil and the door.
Here that give us the main coordinate directions. And what we can do is we can measure the pencil using this coordinate system. All right, so it looks like this pencil is made up of 2 yellow arrows, 1 green arrow, and then 2.
Why do you need the green arrow? You can just use another yellow and another blue. What's the point of the green? The green seems to be perfectly along the pencil. This doesn't make any sense. Just use the green and that's it.
Blue arrows. All right, so we can write this pencil as a linear combination of the coordinate vectors here. Okay, so what we just did here by breaking down the pencil into the coordinate vectors is we measured the pencil's components. The components are just the amount of each coordinate vector that we need to construct the pencil, right? So with this coordinate system, the components are 2, 1, 2. Now I introduced this coordinate system here, and you might think it's a pretty sensible coordinate system because all the direction vectors are the same length and they're all perpendicular to each other, so that's kind of nice. But really, there's nothing special about this coordinate system, right? I could just as easily introduce another coordinate system like this, where the vectors are all different lengths and they all sit at weird angles relative to each other. But
So this is a different coordinate system where the vectors are different lengths. Different lengths. I mean, they're not even perpendicular to each other.
mathematically, neither of these is more correct than another. They're simply just different choices. And so with the second coordinate system, I can sort of do the same thing. I can measure the pencil along each coordinate vector, and I can see that this pencil is made up of 2 black.
I see. Okay. So the coordinate system doesn't necessarily have to be Cartesian. Doesn't necessarily have to be X, Y, Z that are perpendicular to each other and are of the same, let's say, unit length. They could be of, okay, different directions, different unit length. Okay, interesting.
Black vectors, 3 purple vectors, and then 1 red vector. And again, I can write the pencil as a linear combination of these vectors, and I get the
Okay, I'm beginning to understand why there are some videos that I watched, I couldn't understand them. Now I'm beginning to understand those videos. This was missing. This is why it's much better to have a long course than a short course. You would think a short course is better. No, a long course is much better. The longer the course, probably the better it is. Because the least, or the less? I think the less, or maybe no the less steps are being skipped. Very good.
components 1, 3, 2. So you'll notice when I measure the pencil using different coordinate systems, I actually get different components, right? And this is a really important idea. The pencil's components are not invariant, right?
I mean, this is finally what I was looking for. I was looking for somebody who's going to really explain tensors from beginning, not jump into something in the middle. Everybody else I was watching is basically assuming I know exactly what a tensor is, and let me just give you a short review. It's like, no, I don't know what a tensor is. Let me explain it to me from scratch.
They change depending on the coordinate system they use. Okay, so the pencil is invariant, but the coordinates are not invariant. Okay, that's
Vectors are invariant. Vector components are not invariant. What? Vectors are invariant. Like the pens, I don't get it. What?
system they use, right? And then it's 1, 3, 2. So you'll notice when I measure the pencil using different coordinate systems, I actually get different components, right? And this is a really important idea. The pencil's components are not invariant, right? They change depending on the coordinate system they use. Okay, so the pencil is invariant, but the coordinates are.
Okay, the pencil is the vector. Okay. So vectors are invariant, meaning the pencil that we were using as a vector, that's invariant. The pencil doesn't care where we're looking from. What is the point of view? What is the frame of reference? Vector components, but the frame of reference that we're using from which to view the vector wow, I just had a memory that I haven't thought of in so many years. And it's still stored in my brain. It just popped in. Wow, why did it just pop in? What happened? Something happened in an old memory. I was on a bus coming back from Manhattan and I received a phone call. Oh my God. I remember where I was, what I was watching. Why did this memory just pop into my mind? What just happened?
Invariant, right? They change depending on the coordinate system they use. Okay, so the pencil is invariant, but the coordinates are not invariant. Okay, that's a very important idea. So now it turns out that if we know how to change one coordinate.
Why did this memory just pop into my mind? Jesus Christ.
System into another coordinate system, right? So if we know how to go back and forth between these two coordinate systems, then we should also be able to figure out how to change back and forth between these different sets of components. And this process of going back and forth between coordinate systems and components, that's what I'm going to call forward and backward transformations. And I'm going to talk about those in the next video.
That's amazing. Okay. So we should be able to transform coordinate systems as long as we're talking about the pencil. we should be able to quickly switch between frames of reference.
All right, so backing up, what a tensor is an object that is invariant. It doesn't depend on the coordinate system, but its components, which do depend on the coordinate system, change in some special predictable way.
Okay, so the pencil is invariant. So the pencil is a tensor. The components are not. But the components change in a special, predictable way under a change of coordinates. Okay.
That we can figure out using these forward and backward transformations. And this is what I'm going to call the coordinate definition of a tensor. And this definition is actually pretty good. It does get to what the heart of a tensor is. It's an object that's invariant, but whose components change. But it turns out that we can come up with an even better definition. And so I'm going to switch to that one here. So here's our third final definition. I'm just going to read it off.
A tensor, a collection of is a collection of vectors and covectors. Wow. Combined together using the tensor product. Oh, very nice. However, well, you didn't define covectors, and you didn't define, and this is recursive because you're using the word tensor, and you didn't define what a tensor product is. So it's not a complete definition by far.
Tensor is a collection of vectors and covectors combined together using the tensor product.
So unless you're using the definition of tensor from before. Anyway, you didn't define covectors. We know what a vector is. A vector is a tensor. Of rank 2, of rank 1, I'm sorry. So a vector of rank 1, I don't know what a covector is, combined together. So we need a vector and a covector, which I already don't know what those are, and you need to combine them using tensor products. Okay.
So this definition ends up being really nice. It's really short and sweet. There's just one problem. If you've never studied tensors before, you may have heard of vectors, but you've probably never heard of a covector, and you've probably never heard of the tensor product. So the downside of this definition is that we need to put in a little bit of work before we can even understand what it means. But once we understand what all these things mean, it's actually a really simple definition. Tensors are just vectors and covectors combined together in different ways using this thing called the tensor product. So this is what I call the abstract definition of a tensor. So this is really the best definition of a tensor we can come up with, and I'll get to this definition later on in the video series once we have the basics down. All right, and I have a little bonus part here. So for those who do have a calculus background, I'm going to talk about how tensors pop up in calculus, and that's when we see tensors as partial derivatives and gradients that transform with the Jacobian matrix. So you can skip this section.
Wonderful. I don't know what a Jacobian is. I don't know what a Jacobian matrix is. I do know what a partial derivative is and what a gradient is. But I don't remember. Maybe gradient has a mathematical definition. A gradient, it has like a full derivative in it's a multi-dimensional full derivative or something. Yeah, I don't remember.
Section, if you aren't feeling very strong with your calculus skills, it's an extremely interesting use of tensors, and it's very important for the curved geometry we might see in general relativity. But if you don't,
well, gradient intuitively defines curvature. A partial derivative defines the topology. So tensor as partial derivatives and gradients that transform with the Jacobian matrix. Don't remember. I think I once learned the Jacobian like in college.
If you're not comfortable with calculus, you can feel free to skip over this part. All right, so this is sort of the end of the introduction. I spent the last two videos just sort of preparing your brain for what tensors are. In the next video, I'm actually going to start doing real math, and we're going to start with forward and backward transformations. So I will see you in the next one.
Welcome to this first real video in my series on tensors. The previous two videos were mostly on giving motivation and background on tensors. In this video, we're going to get started doing some actual real math. So the first thing we're going to learn is forward and backward transformations. These are the rules that let us move back and forth between different coordinate systems. I mentioned in the previous videos that tensors are invariant under a coordinate system change. So understanding how to move back and forth between coordinate systems is going to be really important for understanding tensors. Okay, so let's start off with the forward transformation.
So you cannot understand tensors without transformations. Okay.
So I have two two-dimensional coordinate systems here. The old basis E1 and E2, and the new basis E1 tilde and E2 tilde. So
okay, let's look at what's going on in the universe for a second. Let's first make sure that the audio is okay. Your channel, yeah, the
components and basic.
okay, so let's start off with the forward transformation.
So you cannot. Okay, everything's fine. Everything is fine. Everything is fine. Let's see. They changed the general VC on the Globe Gangsters Mr. Slave gets layelled. But this guy's been here for a long time. I don't think he's actually here. But where is everybody? I don't get it. Why is everybody gone? This server, wow, it's jam-packed.
So you can't just do that.
No one said anything about, I don't know why you cut me off for pixels. I didn't say pixels. I'm talking about measuring an angle in a picture. On how many
How you're
degrees
measuring
there
angle
is
in a
between
picture?
something.
How are you measuring degrees from a picture?
You could use a protractor, a theodolite. I don't know. You could use anything you want. That measure any angle measuring device.
Yeah, we're not talking about the same thing. I thought we were talking about the same thing or not.
Okay, let's see. A concrete introduction to tensor products. Mu prime math. So this is like tensor, this is tensor product. Okay, at least now we know that we need to know what a tensor product is. The origin of Maxwell's equations. This is great stuff. A friendly introduction to abstract algebra coming up. Group theory. Deriving formula for centripetal acceleration from angular velocity in 5.5 minutes. Bare knuckle. What is so special about tensors? Topology mathematics. What is topology? Exploring shapes, spaces, structures. Method to find principal stresses in 3D. MECMAT. Triaxial stress. Finding principal stresses. Hurricane Helen aftermath in North Carolina. Yeah, I mean, people don't have an incentive to build to build normal houses that withstand these meaningless hurricanes. Like you can build like a skyscraper that could easily withstand a hurricane. You can just sit at home and have a romantic dinner while you have a roaming hurricane outside. But for that, you need permission to build, and they're not going to give you permission to build. And when everything is completely wrecked, they're going to give you money to rebuild, but they're not going to either give you permission to build a skyscraper, and you don't have an incentive to build. Like, why build a skyscraper? You can build a normal house that when it gets wrecked, they'll rebuild it for you. The government rebuilds it for you. So why do you need to worry about it? Don't worry about it. Don't worry about it. We got you covered. The government's got you covered. The government is going to rebuild your house because the government is, it has endless money. The impact of Hurricane Helen will hit the whole world. Oh my God, this guy. Let's hear this nonsense.
Spruce pine.
This guy, he's so like, he's a global warming believer. It's like, it's ridiculous.
Is a small town in North Carolina. There's a reasonable chance you've never heard of it, even though in his best-selling recent book, Material World, Ed Conway describes it as being massively important, absurdly, scarily important. This is what he said about it. In the material world, there are few cases where we are so utterly reliant on a single place. There are a few micro-producers in India and Siberia, but nothing to rival the consistency and quantity of the 2 mines in spruce pine. What do these mines produce? The high-purity quartz that is used to advance semiconductors. You know, Those things that are now relied upon, one way or another, for the generation of reportedly 99% of global GDP. That stuff. Conway goes on. What if something happened to those minds?
Yeah, this guy is always looking for any reason to become hysterical. Oh, the universe is gonna blow up. 99.9% of the universe depends on this thing that if something goes wrong, the universe blows up. Well, let's become hysterical. I want you to panic. I want you to panic. What an idiot.
What if, say, the single road that winds down?
If this town gets destroyed, the next day we'll have replacement. We'll deal with it. Humanity always deals with everything. Humanity always finds a way. Jesus Christ.
From them to the rest of the world.
As long as there's no reason to deal with it, they're going to continue mining it. But if it's gone, the world will deal with it. One way or the other.
Was destroyed in a landslide. Short answer, it would not be pretty. Here's something scary, says one veteran of the sector. If you flew over the 2 mines in Spruce Pine with a crop duster loaded with a very particular powder, you could end the world's production of semiconductors and solar panels within 6 months. No high-purity quartz means no Czochralski crucibles, which means no monocrystalline silicon wafers, which
means the universe is gonna blow up. It's like every morning he has another reason to go insane and panic. The universe could blow up because of global warming, because of this, because of that, because of this, because of that. Oh, the universe. Like for him, the universe is so unstable. It's like, look at his eyes. Look at the panic. The panic. Oh, the panic.
Means, well, the end of computer chip manufacture.
Oh, the end is the end. This is the end. This end. It's like every morning he has another ending for the universe. What an oh my God! I don't have the words.
Know it. He continued, we would adapt, find a new process or an alternative substance, but it would be a grisly few years. The good news.
Oh, billions of years, not just trillion. Endless time. Endless time. Yeah, the next morning we'll find a solution.
Nobody has been dusting that very particular powder, whatever it may be, at least not so far. Yeah, but there is some bad news.
I don't have time to waste. I honestly don't want to waste my time. Tensor, no need, professor. Born interpretation of the wave function. Yeah, I don't care about Born interpretation.
In this video, we're going to discuss the Born interpretation of the wave function. Now, in the previous videos, we've been talking about the wave function as a piece of Schrodinger's wave equation, right? H psi equals E psi. And that psi is the wave function, right? So you would set up a Hamiltonian for a system, you would get some solutions in the form of these wave functions, and they would tell you something about the system. In fact, they're a central pillar of quantum mechanics. So I've written up here the central principle of quantum mechanics is that the wave function contains all of the dynamical information about the system that it is describing, right? The Hamiltonian contains operators that are related to the energy of the system, and then the wave function contains all the dynamical information, right? Including, and I think most principally, the particle's location. And that's what we're going to focus on here with the Born interpretation is how do we
Yeah, but you're assuming there is a particle. Why would you assume there is a particle? There can't be a particle because these elementary particles decay into other particles. So it can't be a particle. And they decay sometimes into photons, which are pure energy. So it can't be there can't be a particle in there. Impossible.
figure out from a wave function where a particle is located in space, right? So in order to do that, we use...
You're already interpreting or misinterpreting
the Born interpretation, which this was developed by Max Born in the early 1900s. And he made an analogy to classical wave theory in order to figure out this way to interpret wave functions, right? So the analogy that he made, an analogy to classical waves. Right, what he did here is in classical wave theory, in order to figure out the intensity of a wave, right, I'll use a capital I to denote intensity. That intensity is proportional to the square of the amplitude of that wave, right? So, so if you have a wave, right?
So it comes from classical wave mechanics, analogy to classical waves. So in classical waves, the intensity is the square of the amplitude. What?
Just draw a little waveform here, right? This peak right here, this is the amplitude, right? So if you want to know the intensity of a wave, you take the square of the amplitude. So interpreting these wave functions as waves in quantum mechanics, he basically built up a way to figure out the probability of the location of a particle based on this analogy. So if we're thinking about quantum mechanics, right, we can use the square of the wave function. in a very similar way. Right, so if we want to figure out the probability of the location of a particle, that's going to be equal to the square of the wave function. Right, and in one dimension, we would have the volume element dx. Right, so integrating over this probability distribution would give you the probability of a particle being in a particular region of space. So let's see what that would look like in a graph.
If there is an analogy to classical waves, that indicates that quantum mechanics is classical. I mean, we keep coming up with classical indications in the quantum realm. That should give us an indication that the quantum realm is classical.
So I've drawn this plot here. The x-axis is basically the location, right, x. And what I've drawn out here is the square of the wave function. This will be a probability distribution, right? So plotted here in green is the square of the wave function. And let's say that we wanted to figure out the probability of the particle being located in this region of space dx. What we would have to do is denote the points in space x and x plus dx. That would give us a region.
The question is there a classical analogy in the classical realm where you would use the wave function for the probability to finding something about the wave?
Region of space to look at, then we would have to integrate over that region in order to figure out the probability, right? If we integrate over this region of space, that gives us the probability of the particle being in that region of space. Now we have to be very careful when we talk about these things, right? We can't say the particle is located at x. We have to say, it has a 75% probability of being located at x, right? It's just the nature of Schrodinger's equation that there's a certain level of, stochastic randomness associated with this. There's a certain level of, probabilistic nature of the equation. Now we also have to be very careful with wave functions because wave functions can be complex. They can be complex functions, complex numbers. So when we say we're taking the square of the wave function, if we're being really precise, we're really taking the square modulus of the wave function. What that means is that you're going to take the wave function and you're going to take the modulus of the wave function times itself again, right? Dx. So this is, kind of review your either linear algebra or just your complex numbers from traditional algebra. It's the same thing, right? So if you have a complex function, you have to take the modulus of it, right? So this is technically known as the square modulus. So square modulus. And when we go through a few examples, you'll see how it's done. But feel free, if you don't remember how to do this, look back at some math, figure out how to take the modulus of a function, modulus of a complex number. If the function is real, if the number is real, then you can just take the square just as you normally would. But we have to be very careful because wave functions can be complex. They can include imaginary numbers, right? So you would look at the wave function, you would square it, you get this probability density, you figure out which region of space you're interested in, and then you integrate over that region of space.
Notice that there's no attempt at a mechanical explanation of what's going on. No attempt at a mechanical, no one is bothered the least bit that there's no mechanical explanation. They're just moving along. Let's move. There's no time. 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 No time. No. We have to move forward. Move forward. No time. No time. No time for thinking. No time. No time. We're busy. We're busy.
Space to figure out the probability. Now this can be extended to 3 dimensions. So if we're looking at this in 3D, right, if we're looking for the probability, then that would just be the square of the wave function. Obviously, this wave function would now be a 3-dimensional function, right? So we'll have a volume element, and instead of just dx, we'll have dx, dy, dz. Now, in this course, I use the notation for just a general volume element, because you can have dx, dy, dz, you can have dr, d theta, d phi, you can have different coordinates. So when I'm speaking very generally, I'll use the Greek letter tau to denote all coordinates, right? So what I'll do is instead of saying dx, dy, dz, I'll just say d tau. And tau just is a shortcut to mean all coordinates. Right, so whatever you got, dx, dy, dz, dr, d theta, d phi, whatever your coordinates are, we're looking at all the coordinates when I say d tau. So whenever I'm introducing something just very generally, I may use this notation of d tau instead of using the specific Cartesian or spherical coordinates. So just be on the lookout for that. Now, what this means, trying to visualize this like we did in 1 dimension, what would this mean in 3 dimensions? Well, what we'll be doing is taking a certain region of space, right? Just like we did here, we're taking a 3-dimensional region of space, chunk of space, and trying to figure out the particle's probability of being in that region of space. Now, right now, since we're talking very generally, and this probabilistic talk might not seem very useful, but you'll see that it ends up being very powerful when we're trying to figure out things in quantum mechanics. You can use this, these probabilities of locations in order to figure out some very difficult and hard problems. Okay, so within the Born approximate or the Born interpretation, wave functions have to have certain properties in order to be valid, acceptable wave functions, right? So I'm actually going to erase this plot here so that I can draw these out or write these down. Right, so there are 4 criteria that I want to highlight, 4 properties that wave functions have to have in order to be valid, right? So 4 properties.
You didn't clear the blackboard. It's a digital blackboard. Just draw a black rectangle over it, or just select it and delete.
Wave functions must have. Right, and this is specifically what they must have in order to be valid within the Born interpretation. So what you'll figure out is something.
What do you mean? The wave function? I don't understand. Let's see.
Sometimes there's, solutions that would work as solutions to Schrodinger's equation, but those solutions may not give you a valid interpretation with the Born interpretation. So you really want to make sure they have these 4 properties. So the first one is that they are square integrable. So square integrable. And all that means is that you can integrate the square of that function. That should be obvious here because we're going to have to integrate over the square of the function in order to figure out the probability here, right? So it has to be square integrable. Also, this leads to a property called normalization. A wave function has to be normalized in order for it to be interpreted in this fashion. That's something that we'll talk about in a future lecture in this unit. But just be on the lookout for that. One of those properties that a function must have is that it must be square integrable in order to fit with the Born interpretation. The second is that it is single valued, right? The function must be single valued. Right. So the reason that is because you can't have two probabilities of in the same region of space, right? If I specify a region of space and I say that it has a 40% probability of being located in that region of space, it can't also have a 50% probability of being located in that region of space, right? That's not how probabilities work. So the function has to be single value, right? You think about, heads or tails, right? You can't say, a coin, if you flip it, it has a 50% chance of being tails and also has a 20% chance of being tails, right? Doesn't make sense.
It doesn't make sense. So you agree that we're trying to make sense of the universe. But you keep saying, oh, but quantum mechanics makes no sense. Oh, well, it doesn't need to make any sense. It doesn't need to. Quantum mechanics at its essence makes no sense. But yet, we need to make sense. But it makes no sense. Yeah, there's no contradiction. Yeah.
If we're speaking in probabilities, these functions have to have single values, right? They have to be single value functions. The third property that it must have is it must be continuous at all points in space. So continuous at all points in space.
Yeah, we're not at all contradicting ourselves. And simultaneously, we are contradicting ourselves. And simultaneously, that's not even a contradiction. Yeah. Welcome to the weird universe. It's not magical. Yeah. Totally not magical. Yeah. No, this is not magic.
Space.
It's just weird.
Right, so any defined points where the potential is continuous, this function must also be a continuous function, right? So no jump discontinuities, stuff like that. It has to be a continuous function at all space. And the fourth one is that the first derivative must be continuous. So the first derivative must also be continuous at any point where the potential is continuous as well, right? So we got first derivative must be continuous. Okay, so these four properties, square integrable, single value, continuous at all points in space, and the first derivative must also be continuous. These four properties, if a wave function meets these four properties, it's an acceptable wave function.
You need to protect your microphone, like you're blowing up every time you say P in plosive letters.
Within the Born interpretation. So let's look at a few example plots and see if we can figure out if they meet the Born interpretation or not. And if not, what's...
So I see that Israel is being attacked now by Iraq. There are Iranian-backed Shiite militias in Iraq. So I don't think, I think the way Israel has to deal with this is, if it wants a military solution, so it needs to be much more violent. It can't take its time. It needs to completely flatten, I would say, at least the southern part of Lebanon must be completely flattened. Like, no human should be allowed, like, in a buffer zone of Lebanon. Maybe including Beirut. Now, Israel might need to just go into Lebanon, take over, declare Lebanon an Israeli territory or something, and just rule over it. Just declare it a military rule. Like, we can't have you guys control your own country because you're declaring war at us. So that's the end of that. So no more Lebanese freedom. Lebanon becomes an Israeli territory. That's it. And just flatten the place, send everybody running away. Go away. Go to other places. Do that with Lebanon. And let people know, you're going to fire rockets at us. We're going to flatten your country and declare it a temporary military zone. In time, we might annex it. So you know what the solution is? Don't fire rockets from your country. How about that? Well, if you want to keep your freedom. Now, if you don't want to keep your freedom, so Israel will just come take over. And that's the end of that. How about that? Now, the next step is Syria. Syria keeps supporting Lebanon, attacking Israel. All right, that's the end of Syria. Israel should go into Syria, and that's the end of Syria. Syria becomes an Israeli settlement. Next. Who else wants, right? Jordan is okay. Jordan is defending Israel. Jordan is fine. Iraq. Next step, Iraq. Well, just conquer the region and done. Like they're not gonna let Israel just live in peace. You know what? That's fine. Just take over the Middle East and done. It's like Israel wants to have a tiny, tiny sliver piece of land. No, no, no. We're not going to allow you. Oh, okay. You know what? Then Israel doesn't have a choice. It has to conquer the Middle East and send everybody running out. Get out. It's now Israel. Goodbye. You had your chance. Anyway. All right. What are these? Right. So this is not this is discontinuous. He said you're not allowed to. This is not I would say this is also discontinuous. I think this is continuous, but there's no derivative at this point. This is undefined, and this is not single valued, and this is also discontinuous. There's no value here. This is this. Is this? This is also there's no derivative at this point. There's multiple problems here. Let's see what he says.
Right. So let's look at A. So A, this is the function that I've plotted here for A, and let's see if we can figure out if it's a valid function for a valid wave function within the Born interpretation. So the answer is it's not going to be a valid function. But what is the reason? Well, the reason is that it's not continuous, right? This function has this huge jump discontinuity located at this point, so it's going to be an
okay. But this is very nice as an abstract math class, but this is not physics. This has nothing to do with physics. You're not talking about the universe. You're not explaining the behavior of this universe. You're just giving up. That's what modern physics is. It's like, let's give up. We assume the speed of light is a constant. Nobody knows why. We're just going to live with it. And that we're just going to assume gravity. No one knows why it is. We're just going to assume it and move along. And quantum mechanics, we don't know why it behaves the way it does. We're just going to assume it and move along. It's like, that's not science. That's not science. None of this is science.
Invalid wave function, or invalid wave function within the Born interpretation. So the answer here is no, because it is not continuous. Okay, so let's look at B. So B is this function. It comes to a little cusp here and then goes back up. So it's decreasing, comes to a cusp, and starts to increase again. So if you remember from your early calculus work, any function like this that goes to this cusp, that's going to have a non-continuous first derivative, right? So if you look here, this derivative at this point, because the first derivative have a flat point here, right? So why would this one x here, right? For probability distribution, probabilities for the same region of space. And then it comes back down from infinity and drops back down into the region of space here. So this is also not going to be acceptable as a wave function, because one of the other features here is that in order for it to be continuous, it has to be finite within the region of space defined, right? So this one is obviously not finite within the region of space, so it's not going to be acceptable. So no, not finite. Function can be infinite as well, but anywhere where the potential is continuous, the wave function also has to be continuous. So so for this case, since it's not finite within a region where the potential is continuous, this is not going to be an acceptable wave function. Okay, interpretation, what it means and how we actually apply it.
Where did he say finite? Properties are square integrable, single valued, continuous, all points in space, first derivative. He didn't say that it has to be finite. Maybe square integrable? What is this thing about not finite? He didn't say it has to be finite. I mean, it's a nice, you could have said it has to be finite. You didn't mention it.
Okay, moving on to the last one, right? So in this last one, we get a sharp increase in the wave function. It goes all the way up to infinity, and then it comes back down from infinity and drops back down into the region of space here. So this is also not going to be acceptable as a wave function, because one of the other features here is that in order for it to be continuous, it has to be finite within the region of space defined.
So it's not continuous. Five comments. Okay, I'm not gonna waste my time. Okay, whatever. It's fine. It's fine. Oh, roundup. In 2 hours. Elastic, AP physics, conservative forces and potential energy tensors. She ruined her life for no reason. They're poking their noses together like little kisses. It's very interesting. They smell each other and then they lick. The purpose is to taste and to pet. They don't have any way to pet, so they can only lick each other. It's amazing that a lot of animals do this. They use their tongues to appreciate.
Hi, you guys have been out to my house twice today, and then most recently the deputy talked my wife into letting me in the house, and then she locked me in the garage, and I tried to break my arm when I was trying to get back inside.
What's your address, sir?
6184 Kenks, Kenks Drive.
Fun fact, a prison in Brazil has swapped their guard dogs for guard geese. The geese monitor the green space between the inner fence.
When this guy decided to take a cool dip in the pond, a swan came flying out of nowhere, aiming directly toward him, making him instantly jump out while his friends laughed hysterically. When this guy
in September of 2020,
when this guy decided to take a cool dip in the pond, a swan came flying.
Yeah, they dip in these ponds as a Christian ritual.
In September of 2023, sensors across the entire planet picked up a strange rhythmic hum that lasted for 9 days. At the time, they found no earthquake or volcanic eruption to explain it. But now, 1 year later, scientists think they finally found the cause. While reviewing survey photos from the Dixon Fjord in East Greenland, they noticed that the side of an adjacent mountain had disappeared. From satellite imagery and computer simulations, they determined a landslide of about 60 million metric tons of rock, the equivalent weight of 6,000 Eiffel Towers, had crashed into the water, producing a tsunami 200 meters tall. As the tsunami raced across the fjord, it reflected between the steep rock walls, stabilizing to a 7-meter high wave that continued to bounce back and forth for 9 days. In all likelihood, this will probably happen again. We just don't know when. But because these events last a while, maybe next time we'll see a whole new extreme sport emerge. Fjord surfing, anyone?
I'm seeing Cuddy. Generally without her clothes on.
I'm gonna go check my office for whoopee cushion.
Weird, they're like throwing hay on top of.
What happened to Float and Grill after Shark Tank? In 2021, entrepreneurs Mikey and Jeremy entered Shark Tank to pitch their unique product, a floating grill designed for cooking on water. The duo sought a $200,000 investment for 20% equity. Mikey came up with the idea after a day at the sandbar, realizing there had to be a better way to enjoy meals without soggy sandwiches. The sharks were initially skeptical. Despite this, guest shark Daniel Lubetsky saw potential in the product. He offered a $200,000 investment for 50% equity. After negotiations, Mikey and Jeremy secured a deal for a $100,000 investment for 22.5% equity, along with a $100,000 loan at 7%.
It's very interesting. So, investment and acting. So you basically need to learn acting, or at least if you know acting. Acting has its use.
What are the animals on Earth with the longest lifespan? Starting out strong, we have elephants, parrots.
Every morning when this person is on their way to work, they see the same seagull standing in front of this convenience store, waiting for the perfect moment to steal a sandwich. And after the door is open, it heads straight for the sandwich sitting on the bottom rack. It then proceeds to poke at the packaging almost like it's done this before, but this time as it tried to make its getaway, the seagull wasn't able to trigger the door sensor. And just when he thought he was caught, that's when someone walking by helped him out by triggering the sensor for him, acting as the perfect accomplice for this high-stakes recovery.
Did you know that Concorde had the smallest windows of any commercial jet? They weren't much bigger than the phone that you're holding right now. Why is that? Well, Concorde was designed to travel at Mach 2, or twice the speed of sound. But when you fly that fast, air resistance becomes a problem, increasing drag and fuel burn. To combat this, Concorde flew at 60,000 feet, where the air is thin. But this brings a problem of its own. As you ascend, the difference in air pressure between the inside and the outside of the plane grows. This means the air inside the cabin pushes harder and harder on the walls of the plane. If your fuselage has any structural weak points, this can lead to an explosive decompression. Now, the windows are a structural weak point on any...
As this man was walking down.
If you chip a piece off of your tooth, a dentist might shave down the surrounding area. Then a bonding material that matches your tooth color is applied and shaped to match the original appearance. Once the shape is near perfect, a special light hardens the material, making it as durable as the tooth. Finally, the dentist polishes the tooth to blend it seamlessly with the others. If you chip a piece...
This new photo from the James Webb Telescope is stunning, but that's not what space really looks like. If you flew out into space and looked at the...
She's hot.
When this elephant suddenly charged the safari vehicle, it was too late to drive away safely. So the tour guide banged on the hood and stopped the attack. But if loud noise works, how come other tour guides don't use it to prevent attacks? You see, elephants attack for several reasons. This elephant was not familiar with the vehicle.
These are pests. They shouldn't be allowed to exist on our planet.
Ever wondered how crucial machine parts become so tough and long-lasting? Engineers use a process called induction surface hardening. It's essentially a combination of heating and cooling. This technique uses induced heat and rapid cooling, or quenching, to increase the hardness and durability of steel. With induction, only the part that needs to be hardened is heated. Induction is used to harden various components such as gears, crankshafts, camshafts, drive shafts, torsion bars, rocker arms, and more.
After this man adopted a baby cow, he thought that his dog named Bandit would love to meet.
This is why Song Hong Yin is one of the most respected soccer players of all time.
Earth is about to get an upgrade, a second moon, a mini-moon. Using the Asteroid Terrestrial Impact Last Alert system, scientists have discovered a small asteroid known as Object 2024 PT5, or just PT5 for short, that's hurtling towards Earth. The researchers responsible for this discovery were able to use PT5's current size, speed, and path to predict its future movements. They found that it was going to come close enough to Earth to become bound by Earth's gravity, briefly becoming a tiny companion to our moon as it follows a horseshoe path around our planet. This event is predicted to happen on September 29th, with PT5 exiting its orbit around the end of November, sending us back to being the only mono-moon planet in our solar system. This news has been met with a fair bit of skepticism.
We should try and capture it. So one of the ways, I mean, this is something we should look into as soon as possible. We should have a moon-based mass accelerator. Now, using this mass accelerator, we can fire projectiles at any incoming object. This could save humanity. This is the most important project. And you could use it then to fire at this asteroid to slow it down as it's incoming so that it will be captured by the Earth or the Earth moon or the moon so that we can harvest it. This would be great. I mean, to have another moon is very convenient.
The most amazing thing happened.
Just like Paperboy, girl. Let me see it, Demario. Back up.
This movie is a true life story that is based.
This customer called in with a gas leak and everyone else told her she was crazy. And I was about to too, but it turns out she wasn't. She started smelling gas in her home. So she called a plumbing company and they came out, checked for leaks and found nothing. So they told her, well.
Wait, plumbing takes care of gas leaks?
oh, there's nothing we can do. But she kept smelling it, so she called another company. They came out and said the same thing. So she decided to call the gas company instead. But they told her that it was this ball valve that you see. And so they replaced that, but she still smelled the gas in her house. So she called the gas company again, and they said the same thing as the other companies, that there's no leak, there's nothing they can do. And I was also not smelling anything anywhere. And she was watching me run all my tests, and I could tell she was getting really frustrated because I wasn't finding it. Not frustrated at me, but frustrated nobody was able to help her out. But I've been married long enough to learn a few things, and one of those being women have really great intuition. And
It's not intuition. She might be she lives there and she's sensitive to smell. Like, I'm very sensitive to smell. I'm so sensitive. Like, the least bit of tiny smell drives me insane. A lot of times people tell me we can't smell anything, and I can smell something, and I lose my mind with these, even the most minute smells. So she's sensitive, and she lives there, so it's not all the time. Anyway, isn't there a way to check it? Even if you move in with a tiny torch, right? There's no problem. It's not going to explode because it's outdoors.
shouldn't downplay their feelings. Trust me, that's a bad idea. But then it dawned on me what it could be. Since she was smelling it in the return, even though I couldn't, to open up the unit outside and see if the valve was leaking. And turns out that's exactly what it was. And when I told her, I've never seen someone so relieved to find out that they had a gas leak. This customer called in with...
That's a detector. Is that a detector? Or is it a sound detector? I don't get it. You didn't show the leak. You didn't prove there is a leak. $5,000 later, finally fixed. Oh, it's frozen.
This is the shortest game of Magnus Carlsen's chess career. We're in India in 2000.
Have you ever wondered what would happen if our Earth had rings like Saturn?
This is some of the craziest aviation footage I have ever seen. This plane was modified and tested for use in a hostage rescue mission in Iran. The US military was planning to use rockets to land and take off from this stadium in Iran during the Iranian hostage crisis in 1980. The plane was modified with 58 rocket pods, with sets pointing forward to slow the plane down, another set facing down to decrease the descent rate, and finally another set facing backwards to provide a boost on takeoff. However, on this occasion, the initial rocket pods firing above the cockpit blinded the pilots, who, in confusion, ignited the second set of forward-facing rockets. This reduced the plane's forward velocity to near zero, and without the downward-facing rockets firing, the plane plummeted down onto the runway, causing the wing to buckle and break. I got to experience one of these rocket-assisted takeoffs in the Arctic, and you can learn all about the plane by clicking this link. This is some of the craziest aviation.
When a store employee gave food and water.
This is one of the strangest encounters I've ever had.
Halley's Comet is named after Edmund Halley, an English astronomer who predicted its return in...
In this case, the length of the crank arm is less than the radius of the wheel. If you pull forward, the wheel rolls forward. In case 2, the length of the crank arm is longer than the radius. In this case, if I pull on the string to the right, look what happens. The wheel moves to the left. In our final case, the length of the crank arm is less than the radius of the wheel. If you pull forward, the wheel rolls forward.
How is that possible? That doesn't make any sense.
So I have some really dirty lead, and it needs...
This gamer is so...
The Very Lightweight Torpedo, or VLWT, is a promising new product developed by Northrop Grumman and is entirely different from the United States' main short torpedoes like the Mk-54 or larger similar torpedoes. This new torpedo is much more compact. While the Mk-48, the primary torpedo used by American submarines, weighs 1,676 kilograms, and the lighter Mk-54 weighs 276 kilograms.
This biker was awarded $65,000, and it's all because the officer drew his gun for no reason.
What an idiot.
Have you ever wondered if your cat...
This man was competing for a gold medal when all of a sudden his bike chain broke. And what happened next was...
Hey, animal lovers.
I got to experience one of the wildest takeoffs of my life in this crazy thing, an LC-130, a modified C-130 that has skis to allow it to land on rough snow in the Arctic. But the most insane modification installed are these JATO bottles. They are just rockets that can be attached to the side of the plane to give it a boost on takeoff. We landed in a remote ice core drilling
I wonder if they're reusable.
site to resupply their scientists. It was negative 40 degrees outside, so we needed to get back off the ground as soon as possible. As we barreled down the makeshift runway, it was basically impossible to know what was going on outside, but as we started bouncing on mounds of snow, it became obvious that we overshot the runway. With the skis plowing through snow, the pilots were struggling to get up to speed and take off. And then this happened. The rockets were lit and we got off the ground. We made an entire video about this crazy plane that you can watch by clicking.
This seal broke into a marine biologist.
Oh, man cub.
Thank you for being here. Thanks for having me. M&M, pieces of advice for the kids. Number 5, keep it real. That's right, keep it real.
Permission to approach the bench.
The worst alphabet book ever. That's what P.
Oh, frozen star. That's my theory, that inside it's just a neutron star.
What's going on inside a black hole is one of the biggest mysteries of physics, if not of science overall. If physics was running for president, it'd say, nobody does mysteries better than me. Unlike most presidential candidates, it'd be simultaneously right, wrong, and completely missing the point. The worst part is that the question of what's inside a black hole might well be an entirely unsolvable problem. But in a new paper that just appeared, a group of physicists says they know what's going on, and it's much stranger than we thought. The new idea is also an old idea, namely that when matter comes close to forming a black hole, it turns into something entirely different. It makes a phase transition, much like the transition from gas to liquid, but in this case, the matter transitions into one big quantum state. This state, so the idea, generates a new type of internal pressure that will stabilize it just above the event horizon. The resulting object looks very much like a black hole, and the difference might be hard to tell by observations, but it doesn't have a horizon. Similar ideas have been proposed several times before and go under names such as fastballs or polymerization, or in this case, frozen stars. The nice thing about these ideas is that they solve a big problem with black holes that Stephen Hawking left us with, namely, how do black holes get their entropy? You see, we know that entropy can't decrease. So if we take something with high entropy, like all those old cables you're collecting in that box in your basement, and we throw that into a black hole, then the entropy of the black hole has to increase. But entropy is basically a measure of how many different ways you can arrange a system. There are lots of ways you can stuff your cables into the box, so it has a very high entropy. A black hole, however, is the simplest possible object that you can imagine. It's a perfect sphere without any features. So how can it account for all those cables you've thrown in? Well, this is where the fastballs and strings enter. The idea says that black holes don't really exist. There's just this big quantum thing that can be built up in many different ways, and that gives you a very high entropy. The new thing about this paper is now that they calculate the probability for a collapsing ball of matter to...
I mean, I would say that from the outside, I mean, there's a difference between the outside and the inside. From the outside, it looks very simple. I don't know. I'd have to think about it.
TikTok. Time is passing, and still no military response from Israel to the 200 ballistic missiles fired by Iran on Tuesday. Arrogant Iranian rhetoric is filling the void.
I mean, Israel is flattening Lebanon, and Lebanon is basically an extension of Iran. So Israel needs to flatten Lebanon, then flatten Syria, then flatten Iraq, and then flatten Iran. One by one, like, you know, as long as Israel keeps moving forward, it's fine.
Western allies are falling over themselves to talk Israel out of self-defense. Why nothing yet from Israel? The New Year holiday, psychological pressure on Iran, or plain old-fashioned dithering? But at least after the death of Nasrallah, the Hezbollah job application queue are receiving a pounding in Beirut. What's next, and how much longer will we have to wait to find?
These guys are obviously gay. Khamenei praises October 7th. What a loser. Doesn't this guy have a life? Like, why do you care about the Jews show so much? Why do you care? Get a life. Get a life, you little imbecile.
All particles are described by what we call a wave function.
But not by the imaginary part. You need to ignore the imaginary part. It doesn't mean anything. It's just a convenience for the math, for manipulations. It has no meaning in the universe. Schrödinger used the wave equation, assuming the electron is a wave. The imaginary part is just a convenience. It needs to be ignored in the solution. It's not part of the wave.
Every possible measurement we can make on a particle is described by what we call a quantum operator.
I don't get it. Like, I hear all this talk about math. There's never a discussion about actual measurements. They talk about measurements when they do the math, but they don't actually do measurements. Like, no one ever discusses a measurement.
A quantum operator is...
What is this? What are you showing me? What is this? What's going on here?
It's a mathematical operation on the wave function that produces another function.
What's the point?
Each type of measurement is associated with its own unique mathematical operation.
How is this related to real life? What is this nonsense? Don't worry if you don't understand these equations. I mean, every equation, you should be able to show me every equation with some computer simulation. And the simulation should simulate something from real life, like the real behavior of an electron. But I never get that. It's always just mathematical equations and abstract simulations.
When a quantum operator is applied, the new function that results typically has a different shape than the original wave function. But in certain special cases, the new function has the exact same shape as the original function, except for the fact that its amplitude has been scaled up or down by the exact same number everywhere. The amount by...
It's a complete waste of time. I'm not interested in games. I want to understand this universe, and this is not helping me understand the universe. This is helping you obfuscate you not understanding this universe. Rare Khomeini speech. So Khomeini gave a speech.
Just like a weird new atheist. By the way,
or so of the aircraft in the squad are rockets that have displaced 60,000 people. I was like, I thought that was going to be shit. It looked shit. Oops.
This is from 3 hours ago.
I thought it was
Okay.
one of those things where.
All right. All right. Let's see what's going on here. Still no one's showing up in this server. Hey, how is everyone? Does anybody want to talk about physics, my theory of ether?
Bro, did anybody else get their account limited today? I got a strike from Discord, bro.
Show me.
Super whack.
I have a friend who got a strike.
I can't do anything except get into a VC. I can't text. I can't DM people. It sucks.
Does it give you a timeout? Does it say like when it's...
Yeah, I can't come back. I can't do anything for 24 hours. Yeah.
All right, just give it time. I don't know. I mean, like I tried once talking to tech support, and it's pretty useless. Anyway, does anybody want to?
Yeah, I
Yeah, go ahead.
yeah, go ahead, bro.
Okay, so
No, go ahead.
does anybody want to talk about physics, quantum mechanics, general relativity, special relativity, ether theory, philosophy of physics, philosophy of math? What is math? What is science? I guess nobody.
What the differences between real science, the physical and natural, or the theories in opposition to reality?
I mean, I don't know what you just said, but I have my own definition of science. So my definition of science is that science, a scientific theory, must be mechanical. It can't be some abstract probability, wave function, stuff like geometric. No, no, it has to be mechanical. It has to be a simple mechanical explanation of some phenomenon that we noticed in that we noticed. If it's not that,
In reality, right? In
yeah,
reality,
yeah, in reality, like if you're
seemed like you didn't want to say it.
what,
Proceed.
like what I'm saying is that if your scientific theory must be simple, mechanical, intuitive, causal. It should be understandable to a little baby. If you
That's the thing. If that's
Mhm.
the thing. If it's a scientific theory, it's not real science, is it?
No,
Because
no,
science proves things, correct?
no. My This is my definition of science. I have my own definition of science.
Oh, I thought we were talking about the definition. My bad.
I mean, I don't think there is a definition of anything.
Is it isn't a scientific theory after is been through the scientific method and it's been established as a scientific theory?
Negative.
I mean,
Actually, the scientific theory is that's what's supposed to be. It's being established. It's been already done through. It's been through the scientific method multiple times, and then it has been established as a theory.
No, that's not correct.
no, no. Wait. So I have my own definition of science. So I adhere to the scientific method that your theory must make a prediction, and then you test the prediction and you validate, and if the prediction is invalid, then you fix your theory and again make a prediction, again test it, validate or invalidate. It's so I agree with that part. All I'm saying is that a scientific theory must be mechanical. You can't like, so by this I would say that like the special theory of relativity is not a scientific theory because it's not mechanical. So Einstein postulated that the speed of light is a constant, but there's no mechanical explanation. He never gave a mechanical explanation why the speed of light is a constant for all observers, moving, not moving, emitter, receiver. What's the what's the mechanism by which everyone observes a constant speed of light? He never proposed a mechanism. He just postulated, which just means he just assumed that the speed of
Right,
constant. Yeah, go ahead.
right. Which made it a theory based off no observation. What he did was apologetic for what he assumed. He didn't calculate, see anything in reality. Yes, you're correct.
No, no, wait, no, no. Uh, I'm saying something very, very specific. I'm saying he assumed the speed of light is a constant for all observers. That's just an assumption. Now, why did he assume this? No, there's no reason, just an assumption. There's no mechanical intuition, no mechanical
Right,
explanation.
right.
Just
I explained it. It was apologetics for something that he never witnessed in reality in the first place. It was his explanation for gravity, therefore relativity, therefore things we don't see in reality. Yes, you're right.
no,
I posted definitions for scientific theory. A scientific theory summarizes a hypothesis or group of hypotheses that have been supported with repeated testing. A scientific theory consists of one or more hypotheses that have been supported with repeated testing, right? A scientific theory represents a hypothesis or a group of related hypotheses which has been confirmed through repeated experimental tests. That is the definition of a scientific theory. You're thinking about a colloquial theory or something that people make an idea and they haven't been through the scientific method. But the scientific theory is already something that already passed. It's after the fact. It's been established already. It's been through the
Not
test.
the facts in relation to the theory, though. No, you can't conclude that. No, but
No,
for
no,
the most
it's
part,
not a
yes, you are
theory.
correct. For the most part, yes, you are correct. But it's the details within the theory which haven't been tested, which
No, but
categories.
we're talking about scientific theory, not just a theory, not just an idea on someone's mind. A scientific
Right?
theory has been through the scientific method.
No, negative. No.
Yes, that's why it's called a scientific theory.
what's I don't see whoever is speaking. What's your name? I can't see you anywhere.
James.
Jemsy?
Is it me? This guy? Is it or is it Jimsy you're talking about?
James, I posted in the live stream text the scientific theory
Oh, I see. I see you.
definition.
Okay. Okay. So, Jemsy, could you fix your mic? Like you're like moving in and out. It's like something is wrong with your mic. Like you're
Yeah,
difficult.
I moved away from it because I was reading, but
Oh,
it's
okay.
should be okay.
Yeah, it's better. Anyway, listen, I don't disagree with anything you just said, but it's incomplete. The way it is, I disagree with it. I don't like it. What you're saying, I include in my definition, but it's an incomplete definition because you didn't specify that a theory must be mechanical. You're saying whatever a theory is, it must go through whatever process. That I agree, but you didn't add the ingredient that for me is
But
critical.
there is theories like the ideas that people make, and then there is scientific theories. Those are different. There's not are not the same. So it's not like an agree or disagree genre. What the scientific theory actually is defined as in the definition. It's been established and it's been repeated by testing and it's been demonstrated to be so, and it's been established as the scientific theory. It's not the theory, the colloquial that you might be thinking about. That you have an idea and it's a theory, and you haven't demonstrated yet, you haven't tested it, but it's a theory that you have. That's not what a scientific theory is. Those are different things.
Right, but okay. That could be your definition, or what for you it might be acceptable as a definition. That's fine. I'm not saying that it's not your definition, but it's not my definition. I have a different definition. I heard that definition. I don't like it. So my definition is I build on your definition. I take your definition and I add one critical ingredient, and I claim that a scientific theory must be mechanical. So, for example,
Yeah, with the experiment and the repeated testing, that's the mechanical part that you're talking about.
no,
Because
no,
a phenomena has been observed,
no, no,
a hypothesis has
no,
been made,
no,
then
yeah, no,
the
no, no,
testing has been done,
no,
the
no, no,
mechanical part,
no, no,
and then the
no,
theory
no,
has been
no,
established after
no,
the
no,
fact.
no, 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 no. I agree with everything you say, except I add another requirement separate from everything you said. I agree with. However, I add in my definition one more requirement. It's completely on top of everything. I don't disagree with anything you're saying. I'm adding one more requirement, and that is the theory must be mechanical. You're not saying that. You keep saying other things that I agree with, but you're not saying the one thing that we have a disagreement on, apparently, and that is that a theory must be mechanical. And that is science to me. And that's the
Can you
most.
define the mechanical part? Can you give an example of what that actually means?
Sure.
Must be mechanical field.
Sure. Yeah. Sure. So, for example, the theory of relativity is not a valid. It's not a valid scientific theory, according to me, because the theory is not mechanical. So there is no theory. So Einstein said, I'm postulating that the speed of light is a constant for all moving observers. Okay, that's not a mechanical theory. I don't even know how to treat it.
Because we can't test it, verify it. That's what you mean? Is that I think that's what we were trying to imply.
No, actually, it has been tested, and he said, literally, he said that Maxwell. Well, he didn't
Never
say.
mind. Never mind.
Yeah, I mean, but he said that we have not been able to detect the ether. So, but I think he meant anyway. It was clear at that point that the speed of light is a constant, but they didn't have a mechanical explanation. And he basically gave up on a mechanical explanation, and he just said, let's just postulate it. Let's just basically introduce it as some cosmic law, which is indistinguishable to me from saying, and then magic. This universe has this feature of magic, and that is that the speed of light seems to be a constant for all observers, which is a magical statement. It's not mechanical. So that's what I mean. So a mechanical theory, for example, when it comes to a constant speed of light, to explain the constancy of the speed of light. So for example, the ether theory, my ether model explains why the speed of light is a constant. Or we can also talk about general relativity. General relativity is not a theory of gravity. There's no mechanical explanation for how the apple falls from the tree. Einstein didn't propose a mechanism, a mechanical cause and effect to cause the apple to suddenly start accelerating towards the ground. Einstein just assumed gravity and just described the way, mathematically, the way it behaves. But he never gave a mechanical explanation as to how gravity comes about. So again, so general relativity is not a scientific theory according to my definition. However, my ether model, in which there is ether flowing towards the ground and is dragging the apple along with it, that's a mechanical theory of gravity. Do you understand? Gemzy, do you understand? Gemzy's gone. All right. Is anybody alive? So everybody's on the server, but no one is talking. S.C. Montreal, you around? He's probably away from the keyboard. Mr. Rockin.
Yes, the relativity, what you said, the relativity theory, that's not a scientific theory because he has not been through the scientific method, right? That's what you're saying?
No, you're not listening.
He hasn't been through the mechanical, the science, the testing part, so it's not a scientific theory.
Of course it's been tested. It's been validated. But it doesn't abide by my requirements of a scientific theory. I have a requirement for my definition, and relativity does not abide by that requirement. It's not mechanical. There's no mechanism for the constant speed of light. There's no mechanism for gravity. So relativity is not a scientific theory according to my definition of science. So relativity is not scientific according to me. It's correct. It's been proven to be correct, but it's not science. It's magic. You can have magic that works, you know. Sometimes, like if you do a rain dance and the rain dance causes rain, then your magic works. That's not science. Do you understand? If you pray and your prayers work, that's fantastic. That's called magic. That's not called science.
Yes, not everything is science. We get that. Not things that happen are not scientific theories. Yes, we know that. Like you washing your clothes, you put it in the dryer, it comes out. You put it in wet and it comes out dry. That's not science. I get it.
I didn't say that. That actually is science. I mean, there is a simple mechanical explanation to how I put my clothes in the dryer and they come out dry. That is very scientific. That's very mechanical. That's actually, I mean, that's a mechanism. You see the mechanism, you know, we understand everything about how the dryer works. I understand everything about how a dryer works, about how to dry your clothes. I have a completely mechanical understanding of how to dry my clothes. Unlike special and general relativity, I've never heard anyone offer a mechanical explanation as to why the speed of light is a constant for all observers. So there's never been a mechanism offered. So
Are we okay today? Because I mean, I know it's talking about washing some clothes and stuff, and now I'm drying some clothes, and now we're talking about dryers and washers and all that jazz. And then I think we're going to talk about some ether theory or some other theories. Mr. Slade, you're an interesting one. You really are an interesting one.
Thank you.
Yeah, Mr. Slave, or whatever your name is. I heard you say my name a minute ago. You said Mr. Rock, and what were you, or did you want to ask me something, or what's going on there?
I'm just looking for anyone to talk to. You're one of the only ones with your mic not muted.
Well, it doesn't show when it is muted. I've got a set of headphones that I just flip it up and it's muted, but you can't tell. But if I mute it on the screen, then you can see the muted mark on my mic. But all I have to do is flip it up and it's muted and you can't hear me. But anyway, that's why.
I see. Okay.
It could be muted. There's just no way for you to tell.
Okay.
Because of this, because of my headphones.
Okay.
Basically.
Okay.
So what are you looking to talk about? I hear you talking about. Are you new to are you a flat earther or what's going on? Give me a little brief summary of who you are, why you're here, and what you're looking for, and maybe we can strike up a good conversation and come to some agreements or some disagreements on some things. Who knows?
Mm-hmm. I am here because because I don't know where else to have a conversation about physics and science and math, and especially my new definition of science and my new definition of, or my new theory of ether. So I'd like to
These are
talk.
all personal. These are all personal theories. Then they're not documented by anyone else. It's just your own personal theories. Is that what we're getting? Is that what you're alluding to here?
Yeah, my definition of science is revolutionary. My ether theory is revolutionary. My understanding of quantum mechanics is revolutionary. My
Well,
Mhm.
that's interesting. Obviously, very interesting. But you do realize that your theories are probably going to be questioned by many people here. There's a lot of smart people in the server. I can tell you that right now. I mean, um, I've been a member and participating in these conversations for about 6 years now. I know a lot of these people here. They've known me for 5-6 years.
Amen. It's the rockin' is rocking.
Right on. Thank you, ma'am. How you doing, Stace?
Doing good, sweetheart. It's good to hear you.
You too. Thanks. So anyway, Mr. Slave, are you? I just got a few questions for you. You think we live on a wet ball spinning, flying through space, or do you believe something different?
Yeah. I mean, I'm not a flat earther. I'm vanilla physics. I'm thoroughly mainstream. I agree with mainstream about everything basically, except for the few things that I mentioned. Like I have my own.
Okay, well,
Mhm.
there's a lot of people that do, and you're welcome to your own ideas and your own theories and all that, and go along with mainstream today. I think personally, if you want my personal opinion, I think that's a very misleading information most of the time. I think that mainstream, like archaeology, they're completely wrong, 100% wrong. They don't know their head from a hole in the ground about the dates of all these archaeological sites, who built them, and this and that. It's all a bunch of bullshit when it comes to that. Now, stuff like physics, that's stuff that is worked out in on paper. You're going to get your physics theories for this and that and the other, and theories has some validation to it. You know what I mean? You can validate some physics. The Earth, there, you cannot provide me. If you can provide me one shred of verifiable proof that we live on a wet rocket spinning through a space ball covered with water. If you can offer me one piece of validatable information, not hearsay, not something like pictures from space, they're even NASA admits they're all CGI. You can go to their website. There's not one real photo that they post. It's all bullshit, and they'll even admit it. And so you can't use stuff like that because it's just unverifiable. Especially when you can go to their website and you can pull up photos and get into the specifics about a photo, and it'll say right there that it's computer generated image. They're not real photos, and so that's a definite no. Don't even try to use it's pictures from space or people on the space station orbiting around the Earth. There's no verifiable information that can prove those things to be true. So, if you've got something, I'd certainly be love to hear it, and I'm sure most people here would too. If you've got any evidence whatsoever that can prove that what we live on is a planet rotating, flying through space in a vacuum. It violates practically every law known to man. Like gas laws are violated. The spinning ball flying through in a vacuum. The second law of thermodynamics, that's a complete violation. Doesn't work on a ball vacuum, just doesn't. Entropy would be instant. The air would completely just evacuate, and gravity has got no hold on the atmosphere. Doesn't do anything to the atmosphere. It's if you believe it does, then again, you'd have to provide actual evidence and proof that that is happening. So if you've got anything at all, please tell me. Everybody here would love to hear it as well. Any evidence at all that we live on a planet.
Right. So I don't really. I mean, you need. I mean, I understand what you're saying, but I'm not
Well,
here.
you'd be the first. You'd be the first.
I'm
to
not
actually
here,
provide evidence.
but
for
I'm not
that.
here for that.
Okay.
That's not
Well, that's
something.
what most people are. There's a lot of people that are. So I just thought I'd throw that in the mix. But just so you know, as I've been here for 6 years and I've never seen anybody provide one shred of evidence that we live on a planet flying and spitting through space. So
Okay.
never happened.
Okay. Look, I'm not here to.
I know. I heard you that. I just wanted to let you know that it's never happened, and that's why I asked you. If I thought maybe you'd have something for us.
Listen.
We would all love to hear about.
Let me just finish. Hold on. Look, listen. I'm not here to change your mind about what you believe. That's not my purpose. I have a different
It's not a
purpose.
belief. I have proof from my evidence.
Well,
I have proof from
it's fine.
I have evidence.
It's fine.
But
But I'm not here to change your mind. I honestly.
Well, you can't do that. But it's all,
Yeah.
it's all good. It's all good. You don't have to worry about trying to change my mind. It's not going to happen.
No.
Anyway, so what? Just tell me why you're here. What do you want to talk about? I mean, what
Exactly.
Obviously, you're here because you want to have a discussion about something.
Exactly. So
what is it? Let's hear it.
Right. So I'm not. Let me just finish the sentence. So I'm not here.
right.
I'm not here to change anybody's mind. I honestly, you could say I don't care about anyone in the universe. I don't care. I don't care what anyone thinks about anything. It's honestly. I happen to be curious about the universe. And I came up with a theory. I came up with a theory of what science should be. I came up with a theory of what the purpose of a discussion is. And I came up with a theory of what causes special relativity and what causes general relativity and what causes quantum mechanics. And I would like to stress test my findings. So I'd like to tell you about my findings, and I'd like you to try and stress test, try and find holes in my theories, try and find contradictions in.
Well, I bet you're gonna find some people here with exactly that.
Didn't you say magic earlier when you said special relativity? You say it's like magic. You said that earlier, didn't you?
Yeah, I mean, if it's not a scientific theory, then it's a magical theory. Like
I'm sorry. You also said a theory of a proper discussion. Like, what's your? I'm sorry. Why are we theorizing a proper discussion? I'm pretty sure it's common sense what a proper discussion would be, but I guess in this world and day and age, it's not. We have to come up with theories for it. I'm baffled.
So, like what, like to me, what is to me the purpose of a discussion? So I've had discussions, and I see that sometimes I'm unable to convince people. So I just gave up. So I just don't care what people think. So my purpose of a discussion is no longer to convince. I don't care what anyone thinks. My purpose of a discussion, therefore, my theory of what a discussion is, well, a discussion is to stress test my ideas. All I care for is my ideas, and I'd like you to try to prove to me that I'm wrong.
This is grand, bro. I ain't met anyone in my life that's like this. This is cool, actually, but not. You are really supporting yourself like on a pedestal, and you're like, I don't care what you think, but I want you to battle me. I mean, your theories of a proper discussion are already flawed. Like you're
Well,
coming from a very egotistical point where you're thinking that you're right, so no matter what, it's everybody else is wrong and you don't care. How is that going to be a proper discussion if you just want to hear yourself talk and you don't really care what people think, or you don't really want to convince anyone and you just don't care? Isn't that kind of like, I don't know, vain?
Well, that's how a
Something.
proper discussion goes, Stace. Is exactly that. You discuss things, and both people have their, their evidence or their own personal theories or whatever, and it's a back and forth. And it takes two people to have a conversation. By the way, Mr. Slave, takes two people. That takes two people's opinions to have a proper conversation. So, in order for you to say you don't care, like Stacy just said, I don't think we're going to be able to have a conversation with you because we're entitled to our opinions as well as you are, and they have to be evaluated as well as yours. And so you can't just say that you don't give a shit about what we got to say. I agree with Stacy. You got to give a shit what we have to say. Otherwise, we don't have much to say to you. You can just blabber on about your theory and whatnot, and somebody will probably end up muting your mic and moving on to a new discussion, because conversations are a two-party thing.
Right. So,
Thank you, Rocket.
but that's not at all what I said. So I am
Well, that's
interested.
how it came across.
Right.
No, it's literally the opposite. So I am here to hear your opinion about my opinion. I don't care about your opinion about anything else except
Well,
for
then I don't have much to talk about with you, my friend.
Do you hear it? It's a double speak. It's just
You know what I
super
mean?
bad.
Yeah, double speak for sure. Yeah, if you don't care what I got to say, then maybe you should talk to someone else, because
that's not what I said. I said I don't
okay,
look.
then it's exactly what you said.
No.
What do you mean it's not what you said? It's word
No.
for word what you said.
No.
You said I don't care what you say.
I didn't say that. That's
You did say that.
No, that's incomplete. No, I don't
Everything's
care.
recorded here, bro. I can back this up and we can play it for you if you want.
Yeah,
to.
that would
It's all
be
recorded, dude.
Well, that would be half a sentence. So I care about what you say. I care about your opinion about my opinion.
Okay, then what's your opinion? Give us one. We're done with this part of it. And then you got some theories. Let's hear one. And then these people will be more than happy to either carry it for you or go along with you.
Okay, so science, a proper scientific theory must be mechanical.
Well, the scientific theory, the scientific method, it was developed back in ancient times by the Greeks. The Greeks gave us a scientific method. It's been around for 4,000 years, and it works very, very, very well. I mean, it validates science. You got to have a hypothesis. You got to have independent variables. You got to have, and they have to be tested back and forth. And the scientific method works beautifully for proving, a theory or a whatever you want to call it, but because it's got to be testable and repeatable and verified, and that's what the scientific method does. It allows you to do all of those things, validate a theory, and if you cannot validate it with the scientific method, then it's probably not worth a shit.
Right. But I see where that led us. That gave us the craziness of quantum mechanics and the craziness of the weirdness of anyway, I'm unhappy with physics, so I don't like this definition, so I changed the definition.
I'm unhappy with academia.
Exactly.
I'm unhappy with, because I think they're full of shit.
Exactly.
They have an agenda that they want to stick to.
No, I
don't believe it. I don't like it.
Yeah, I agree. I don't think there is an agenda. I think just that their definition of science is no good. So I came up with
there's an agenda. They got a paycheck they're trying to protect. There's an agenda. Trust me.
Right.
They got a paycheck.
I
These
agree.
physicists and these
agree.
archaeologists and all these people that got
I
these
agree.
degrees, they got paychecks they're protecting.
I agree. I agree. So I'm offering a fix to this problem. So the fix is that the scientific method must include a theory that is 100% mechanical. So For that reason, special relativity becomes unscientific because it's not a mechanical theory. General relativity becomes unscientific because it's not mechanical. Quantum mechanics
Well,
becomes
I agree with you that those things are not mechanical and cannot be put through the rigorous tests of a regular mechanical theory, and which the scientific method would handle very well. I mean, because you could validate or nullify anything along the way. I mean, I just I don't know where you're coming from with the scientific method, because I think it has basically gotten rid of a lot of bullshit, a lot of cockamamie theories that people believe in, and they can't test them. There's no way to verify what they believe or what they say about the earth and many other things. There's no way to validate these things, and so and thank God for the scientific method, because they're full of shit. Anyway, go ahead.
Can I ask you a question, Mr. Slade? Like your theories for ether, like can you scientifically prove that from the scientific method? Can anything with it?
Look, so
no.
My ether model actually gives us a constant speed of light. My ether model actually gives us a mechanical explanation for gravity. My ether model actually.
Cágate en tu madre, cante cabrón.
Yeah, I agree.
1 second, Jeremy, real quick, sweetheart. Nobody was trying to talk over you. You are definitely roboting, just so you know. Heads up.
Anyway, Mr. Slave, or whatever your name is here, we get it. We get where you're coming from now. So let's hear your theory. We don't want to hear whether it's this, that, or whatever. What is it? What are the parts of your theory? What do you have to offer us for this ether theory? What are you talking about exactly? It's the exact things you're talking about that cannot be tested or are not mechanical or are mechanical or whatever. Give us some information here. You're just kind of just talking about something, and you're not giving us anything to work with. So give us something to work with, please.
All right. So the question that we can start with is, why does the apple fall to the ground? So
well, there's a lot of theories on that. There's a lot of reasons. There's provable things about it. I mean, you've got what they call gravity. You've got electromagnetism. You've got buoyancy and density that cause, like an apple that floats in water, sinks through the air. So it's
because it was right. It was at the moment it has to fall.
Anyway, so yeah, that's testable. There, you can provide several different reasons for why the apple falls. The atmosphere, the medium that it happens to be in, is the apple's denser than the air, so it falls. Throw it in the water, it floats because it's not as dense as water. So, buoyancy and density handles a lot of gravity, in my opinion, because I don't believe gravity is a real thing, not the way they say it is. I think it has more to do with electromagnetism. We live in an electric and a magnetic universe, in my opinion, and I think that's pretty much validatable. So
anyway,
here's some more.
Okay, so the apple falls to the ground. So Newton never answered the question, why does the apple fall? Newton gave us a description. He gave us the equations that describe how the apple falls, but he didn't give the reason. He never gave a mechanical reason. And he actually said that if you think that gravity is mediated through the vacuum of space, then you need to have your head examined. He said something like that, or he wrote it to a
Well,
friend.
I would agree with that. If you think gravity's a real thing at all, you need to have your head examined, in my opinion.
No, but Newton said
at least the way mainstream tries to tell you. because it's the density of the Earth. The core of the Earth is this magnetic molten core of whatever, and the weight of the Earth is what causes things to collect to it. I just don't agree with that. I'm sorry, I just can't. Ridiculous. For one thing, we don't live on a ball, and so the core is non-existent in reality. There's no core to where we live. I mean, there might be a center of something underneath us somewhere, but what it is, nobody really knows. We've only drilled into the Earth 7 miles, ever close to 7.5 miles, something like that. The Kora borehole in Russia, I think it's called, and that's as far as they got. They got down there, and the bit clogged up with some peanut butter type substance, liquid, hot, 500 degrees or something. But the bit just couldn't go anymore. It just clogged up, and they were done. There's no way for them to go and investigate any deeper than that. And so, what's below that is just your guess is as good as mine. They got their theories, and they try to tell you it's this and try to tell you that, but there's no evidence for any of it. So.
Right, but so according to physics, there is no explanation as to why the apple falls. All that Newton gave us is a description of how the apple falls. So you can use
fast,
hold on,
and
hold
how
on.
it gained,
Hold-
just
hold-
terminal velocity and
hold on.
whatever else. I mean,
Wait.
there's
Hold on.
I can't remember the
Hold-
equation about
wait.
things fall.
Hold.
So many
Wait, I didn't
per
finish.
second.
I didn't
All
finish.
right.
All right. So
All right. But you're not giving us anything, no. So give us something, please.
well, you got to let me talk. So it's going to take a long time if for every half a sentence I say, you're going to give a speech. So you got to let me talk. So it's up to you. And
Well, go ahead. Say what you got to say, but give us something, please.
Okay.
Stay shut up, but I expect to have something to work with when you're done.
I mean, you can ask me questions, but as soon as you start telling me your theories, that's what I said. That's not what I'm here for. I'm here to tell you what I think and for you to stress test what I think. I'm here for you to find contradictions in my story, contradictions between my story and reality. I'm just going to tell you a story why the apple falls to the ground. And you try and tell me why I'm wrong. So, Newton didn't tell us why the apple falls. Einstein didn't tell us why the apple falls.
Einstein did tell us why the apple falls.
Yeah, I'm listening. Why? What did Einstein say?
Curvature of space-time.
Why is space-time curved?
Good question.
Yeah, so there's no answer.
What do you mean no answer? It is curved. So what?
Yeah, why?
What do you mean?
That's not an answer.
Science isn't good for why questions. If you want why questions, go ask your minister.
Okay, so as I said, Einstein did not explain why the
Einstein did explain it quite well. Thank you very much. It explains.
Yeah, I'm listening. Why?
Again, the curvature of space-time.
Why is the space-time curved?
Because it is. If you want to ask why questions, you should go ask your minister, not ask it to science. Are you asking because you asking some sort of minister, some sort of God question?
Okay, so I'm trying to present
God.
So I'm trying to present an explanation where Einstein did not present an explanation.
Einstein did present the reason for gravity to function.
I did not stop you mid-sentence. I let you finish each time, and you cut me off each time. So please just let me finish.
Because you are lying.
Yeah, and you keep repeating yourself too, because you keep saying that no, he didn't. He did. Einstein provided a very detailed hypothesis.
Okay, Mr. You can finish your sentence. I muted him, so you can finish.
Thank you. So Einstein, like Newton before him, so Einstein just gave us a better Newton. So Newton just gave a description of how the apple falls, but he never gave an explanation why the apple falls. And we have a quote from Newton, as he said, if you think gravity is mediated through the vacuum of space, then you need to check your head, something like that. Now, Einstein did not provide an explanation. Einstein just took gravity as a given, like Newton before him, but Einstein generalized it with his special relativity, and that's all the general relativity is. It's not a mechanical explanation of why the apple falls. And physics doesn't give an explanation for why the apple falls.
It's totally incorrect. You are
Neither.
totally incorrect. Einstein gives very detailed mathematical reasons on this. If you don't understand the math, that's not my problem. That's your problem. But stop saying that he doesn't do it.
Okay, you keep repeating. You're not.
I keep repeating. Fuck A. All I'm telling you is.
Yeah, you keep repeating, and you're cutting me off and repeating yourself. It's not like you're cutting me off and adding information. I'm just trying to finish my thought.
You've said the same damn thing at least 20 times, and you're lying.
Anyway. So physics does not provide an explanation for why the apple falls. Neither does physics provide an explanation for why the speed of light is a constant. Einstein literally postulated the speed of light to be a constant, meaning he just said it is so. He didn't bother to even question it. He just said that's a given, and from that we have special relativity. He didn't give a reason why. So special relativity is not a scientific theory by my definition. It's not mechanical. Neither is general relativity. So physics today has become a magical philosophy. It's no longer scientific. Physics with special relativity, general relativity, and with the nonsense of the probability of quantum mechanics, they're no longer scientific by my definition of science. They're pure. It's just magic. Now, sometimes you have magic that works, but that doesn't make it science. If your rain dance works, that's very nice. That's not science. It's still rain dance. If your magic spells work, that's fantastic. That's not science.
How do you think the apple got up there in the first place? That to me is more interesting.
You know, that's the sort of question that I get in a dating site. That's usually what chicks ask, but I'll finish my thought. Anyway.
Oh.
Yeah. Chicks don't care why apples fall. They care how the apple got there in the first place. Anyway, so I'll provide you now with a mechanical explanation for a very simple mechanical explanation for why the apple falls. It also explains why the speed of light is a constant, and it also explains quantum mechanics. So
boring.
You don't have to stay here. Or I mean, if you want to.
I'm just kidding with you, man. If you want to throw insults, you got to be prepared if you're going to dish it that you're going to get it back, okay?
I never insulted anyone basically in my life.
Yeah, you did. You were condescending to him about comparing him to a chick and this and that. People are pretty sharp, my friend. They're going to catch every little slip up that you got. And if you're going to it out, be willing to take it because it's going to come.
Oh.
Just don't take it personally and move on with your conversation. Give us what you got. What's this mechanical explanation of gravity? You haven't given us anything yet. Keep saying you have it. Well, let's have it.
Okay, just in reference to how the apple got there in the first place. I'm sorry about that. You're right. I don't want to have a personal back and forth. If I hurt your feelings, I'm sorry. I'd rather not discuss nonsense. I just want to express my theory and get your people's opinion about my theory.
Okay, thank you, sir. You could continue.
Thank you. So the way the apple falls is that there is this universe is filled with a fluid. It's completely filled with a fluid, an incompressible fluid. And that fluid is flowing right now through us towards the center of the planet. And as it is flowing through us, it is dragging us along with it. And it's dragging the apple along with it. And it's dragging everything along with it. And that is what we experience as gravity. Now, this same fluid creates a constant speed of light. To explain why the speed of light is a constant is a little difficult, but I have a paper. I'll just submit the paper to the group. Anyway, so if
I got a question.
Go ahead.
You said you said everything's surrounded by a fluid, like the whole cosmos.
Yeah, it's not just surrounded. Everything is immersed, and all the elementary particles are waves in this fluid. So everything.
All right, hold on.
Mm-hmm.
That's what I'm trying to get. Yeah, because I'm just curious. So we're all immersed in a fluid, and I actually agree with that. But what is flowing downward, right? If we're all immersed in the fluid, right? You're saying that the fluid itself is also flowing, or is there something within the fluid that's flowing, like a wave?
No.
That's not the fluid necessarily.
No. The fluid is flowing into the earth and is dragging us downwards. So,
all right, hold on a second. Hold on.
Mm-hmm.
So the fluid that we're immersed in, that fluid is moving downward.
Yeah, fast at 11 kilometers a second right now. It's
I don't agree with that.
Well, there's a big problem with that to begin with. I'm going to say one thing and then I'll stop.
Yeah, sure.
You got the core of the earth. You're saying that it's going toward the core of the earth. Now that means that this fluid is flowing all directions. The bottom of the earth, from that side, from this side, all toward the core. When it collides in the middle of the core, where does it go from there?
Good question.
It's coming. You say it's coming from all places toward the core of the earth. Where is it going once it gets there? Does it?
Good question. That. Excellent. Fantastic question. So this fluid, when it interacts with, let's say, with an electron, it annihilates. The fluid self-annihilates upon interaction with an electron, with a proton, with the earth, with us, with the apple. So every time this fluid interacts with a massive particle or a massive body, meaning a particle or a body that has a mass, the fluid self-annihilates. When the fluid self-annihilates, a fluid vacuum is created. An instantaneous fluid vacuum is created. So the Earth right now is a vacuum of the fluid. The fluid is, I call it the ether. That's what the ancient ones used to call it. So I'll use the same.
Well, this still doesn't make no sense, sir, because when this stuff annihilates, the particles that in the annihilation are still there. You cannot destroy matter. You cannot just have it magically disappear. That's been proven. Matter cannot be destroyed nor created. It just is. And if you're saying this stuff is annihilating, then where's these subatomic particles going? Where are they going? This thing annihilates itself. It's still all that mass of this fluid. You're saying it's got to have mass. It's got to have. It's a flowing substance. It's got to have matter to it. It's got to have something. And if it annihilates, it's still going to be there, just in smaller pieces. It doesn't make any sense, bro.
Right.
You're going to have all this annihilation happen in the center of the earth, and it's going to build up and build up and build up and build up. Pretty soon, there's not going to be room for anything else because you're all piling all this fluid into one specific spot, the center of the earth. That's not how this place works, bro. The whole universe is not directed towards the earth, and it's not just the area around the earth that's sucking this so-called fluid toward the center. I mean, you can't just have it disappear. It's not possible, bro. That's not how it works. You can't destroy matter like that, have it just be gone.
Right.
You can turn it into subatomic particles, but you can't make it disappear, bro.
Right. So that's a good question.
Unless it's going through a black hole.
No.
Then.
No. That's
well, it depends on what you believe a black hole to be. I believe a black hole is just super, super dense and it sticks to it. Even light sticks to it because it has so much gravity to it that light can't even escape from it. But it piles up, and the black holes, as they mainstream tries to make you believe that this material, as it gets sucked into the black hole, becomes part of it, the dense part. In fact, they said that if your body was being pulled into a black hole, it would be pulling you so hard, so fast that by the time you got there, you would be in a straight line.
Okay.
It would be one atom at a time, piling into on top of one another into the on top of this black hole and becoming part of it. So dense that it's just ridiculously dense. I have no idea how to explain that, but it's so dense that not even light can escape from it. So black holes don't make things disappear. They just make it pile up again.
Okay.
That's what they say.
Okay.
I don't believe it, but whatever.
All right. Look, you're asking a good question. Let me just answer.
Right.
So we know in physics that in general, mass doesn't just disappear nor gets created, but that's in general in our lives, that's a true rule to go by. But we know that cosmologically, that the dark energy is always being added into the universe, for example. And also we know that on the subatomic particle scale, that particles are always coming in and out of existence. So it's our intuition based on our experience that matter doesn't just annihilate, but there are exceptions. So this is such an exception. It's not exactly that. So when the ether interacts with a massive particle, so actually before it interacts with the particle, like an electron, the electron doesn't have mass. So all the elementary particles, before they interact with the ether, they are massless. This interaction with the ether, so the ether self-annihilates, and by self-annihilating, it is endowing these particles with their mass. And this is what's called the Higgs mechanism. So, and by the way, everything I'm saying, I'm never contradicting physics. I agree with everything that mainstream physics says. I'm just giving a mechanical explanation for everything. So, so the ether interacts, let's say, with the Earth and gives the Earth.
Can you correct it?
Can you answer
Can you correct it to theoretical physics? Is what you're talking about?
What do you mean? I'm talking about mainstream physics. So I'm not.
I wouldn't know how you're going to prove this dang theory. I'm so sick of hearing the theory. I've heard it for so many weeks on end. It feels like, what are you talking about? Okay, now you're talking about it's going to self-annihilate. It's going to destroy itself. Done. Annihilate. Okay, how are you going to prove that? I'd like that to be proven, because you're talking about a theory that's going to just go away and it's done, and I'm supposed to believe this shit. Now, how are you going to actually take this theory and do something with it to show me? Because I don't think you're going to be able to show me that.
Well, I'm giving.
Right?
Well,
I just said it was based upon a machine worldview.
Well, so I'm giving
enough evidence.
Look, I'm giving an explanation, a complete explanation for gravity and for the constant speed of light, and for the wave nature of all the elementary particles. And
No, you're not, dude. No,
Thank
you're not.
you.
You're just making shit up, dude.
Thank
Look
you.
at this.
yeah,
And I
Thank
can't
you,
take it
Ryan.
anymore.
Correct.
It's just as
Hold on.
bad as, dude. At least relativity has the math to back it up, dude. Do you even have any math, bro?
Nothing.
I'm
It's
not.
just something that you thought in your room or something. Maybe I got really high one day and I was like, damn, ether could just flow right through me. How am I going to prove that? I mean, it's just like, I understand you have theories in this magical world you want to create. So do I. But if you're going to come in here with like this scientific theory, please have something you can show me in reality that you can prove to me. And right now, it's kind of like you wasted my damn time yet again. And I'm sorry, hon, I'm not trying to be mean, but my head's kind of banging from this shit.
Well,
I can also pick up a pencil and draw some marks on it, and faking gay distance and depths and everything. I learned that at school.
Well, so as I said, currently there is no explanation for why the apple falls and why the speed of light is a constant.
There is explanations, and the thing is, like, people already predicted that people like you would come about because we knew that people would hold on to the globe and steal the ether, and that's basically what you've done. But it's even worse, dude.
Does the apple fall when it's ripe, or when is it?
Anyway.
Oh, reality was again there too.
Anyway, if you people want me to continue, I'll continue. If you want me to leave, I'll leave.
What do you want to do? I mean, are you holding a lecture? What is this?
I'm presenting my theory and I'm interested in feedback. I want to see if you can find a contradiction in my theory.
We're giving you feedback.
I appreciate it. And I'm trying to move forward and explain to you my answers to your feedback so that we can continue the back and forth. I want to stress test my theory. Everything
Do you have a 250 word do you have a 250 word abstract of your theory?
Yes, it's in the side chat.
Okay, nice. I'll read it.
There's 2 papers. The first one that I added is the proof for Einstein's second postulate about the constancy of the speed of light. And the second paper is the gravitational ether, how ether creates what we call gravity. Anyway, so
okay, I'll take a look, man. I have a question for you though. Why do you call yourself Mr. Slave?
That's
also
not,
on your paper, that is.
That's not important.
Why not?
It's not important. Why it's not important either. It's just not important. I want to
Why is it not important?
It's not important. It's just I don't care. I don't care.
Why don't you care?
That's just
He likes to be dominated, dude. He don't want to talk about it.
Wait, no. Don't make projections. I'm just curious.
It's not.
Why don't you care, man?
I'm not here for that.
Projections, yo.
Let's wait and see. Maybe they're correct, but I'm just curious, my friend. Why don't you care and all that? Why?
I want to talk about physics. I don't want to talk about like anything else. I don't want to talk about myself.
Okay, but when we are pursuing the truth, wouldn't human behavior be a part of that?
Not right now. I'm pursuing a very specific.
Are you sure? It could be valid for me to assess your own view of yourself in accord with me reading your abstract through your paper.
You can go to my channel.
Assess people, and let's not assess people next after this. Let's not assess people and their character, and let's go on to words, please. I really need a good conversation to take place. I don't care what it's about, but let's just have a conversation. Thank you.
So, if you want more information about me, I have a channel with like.
What do you think? It wasn't about you. You said I don't want to be about me, and now you make it about you. Again, let's just move forward with it.
What do you think about Ken Wheeler?
Never heard. I don't know what that is.
I think he'll set you on the right track, dude. I'm not a big fan of Ken Wheeler, but regarding magnetism, yeah, he'll set you on the right track, dude.
Well, magnetism is the same problem. Like, how does magnetism work across the vacuum? That's the same problem as gravity. So no one knows how magnetism works, just like they don't know how gravity works. It's the same question that Newton
So you know,
asked.
guys, just
Yeah,
so everybody
it's
knows, this whole
it's
thing
sorry.
he's streaming the whole thing live to YouTube, just so everyone knows.
Yeah, it's really important to build a foundational structure of seemingly all that exists on something that we have no idea about how works. Because dissociating ourselves from actually just experiencing, touching something, and calling it, no, this is a representation of your sensation. That is where we are at right now. And that's obviously where we want to be, where light goes into your eye, and it's turning your world into your ability to not see it upside down, supposedly, while you're also spinning upside down. I mean, everything that you spout through your apparatus and methodologies that don't actually assess the thing, but the concepts pertained to a thing, or its behavior, rather, all of it is ideas. And so when you say that the base that makes up the entirety of your whole worldview, the base, you have no idea about it, and you appeal to this authority of, we don't know, you are actually gaslighting the entire populace that exists in existence, who can actually cope what you're saying. Do you comprehend that?
No, I don't understand anything of what you said, honestly.
Okay.
Listen, let's not do this. Let's not partake. I'm gonna
Stacy,
be my
please.
mistake. No,
Take
I'm
some
gonna be my
peace here.
mistake right now because I literally just can't. I'm pretty sure Rumble. What's up, Rumble? And anyone that's watching on your own little YouTubes that you're recording, I don't really care. It needs to stop. I'm pretty sure that Gia would like a really good conversation. I don't really care if it's about addiction
This
and what
is
you
a
can
really
on your
stop.
life.
This is a
But
really
it
good
sounds
conversation.
like no, it's actually not. I'm sorry.
It is. Why would you not talk about what is being your oppressor? Why don't you want to expose the oppressor so that you can actually have a good life? I mean,
All right, it's a waste of time. No one is on the server. Okay, let's go to mine. It's the Rockin', Gemsy, Amber, Cenas, Jensen, Mordwand. He's on his mobile. Okay, let's get back to, I guess we have no choice. We have to continue our studies. Let's see what's going on here. Project presentation, Maxwell Boltzmann versus Bose-Einstein. What? Disgusting creatures. The bears. I hate bears. Pests. What is a tensor? The deep learning tensor. Helen? Cosmic microwave background. Introduction to Schrödinger's equation. The Schrödinger. I'm becoming a little hungry. Okay. Let's get back to this guy.
So remember from linear algebra that the word basis just means a set of vectors. We're going to get started doing some actual welcome to this first real video in my series on tensors. The previous two videos were mostly on giving motivation and background on tensors. In this video, we're going to get started doing some actual real math. So the first thing we're going to learn is forward and backward transformations. These are the rules that let us move back and forth between different coordinate systems. I mentioned in the previous videos that tensors are invariant under a coordinate system change. So understanding how to move back and forth between coordinate systems is going to be really important for understanding tensors. Okay, so let's start off with the forward transformation. So I have two.
So it's really interesting. So in order to understand tensors, you need to understand coordinate transformations. That's fascinating. One second, I needed to answer. I needed to answer one of my chicks. Let's see. Checking emails. I don't see any issue. Everything is fine. Everything is fine.
Two-dimensional coordinate systems here.
So we're doing transformation.
Forward and backward transformations. These are the rules that let us move back and forth between different coordinate systems. I mentioned in the previous videos that tensors are invariant under a coordinate system change. So understanding how to move back and forth between coordinate systems is going to be really important for understanding tensors. Okay.
Let me check how long we've been streaming. 3 hours. Okay, we're gonna finish soon because I want to eat.
Okay, so let's start off with the forward transformation. So I have two-dimensional coordinate systems here. The old basis E1 and E2, and the new basis E1 tilde and E2 tilde.
What is E1, E2? Is that like X1, X2? I guess. And the tilde is, I guess, Y1, Y2. Okay. Notice, like, the tilde system is not unit length. They're different lengths and not 90 degrees. It's like it's completely bizarre. So old bases, so these are called bases or bases. So E1 is a base vector and E2 is a base vector for the coordinate system, and E1 tilde is a base vector and E2 tilde is another base vector.
So remember from linear algebra that the word basis just means a set of vectors that give us the main coordinate directions for our space. So we have the old and new coordinate systems, or the old and new basis. So the forward transformation will move us from the old basis to the new basis. So how does that work? Well, all we need to do is build the new basis vectors out of the old basis vectors. So let's start with E1 tilde here.
So E1 tilde is going to be some component times a basis vector plus some component times another basis vector. And E2 tilde, right? And now we have to find out these components.
How do we build E1 tilde out of E1 and E2? Well, it looks like we need two E1 vectors and one E2 vector. So I'll just write that in here. Now, what about E2 tilde?
Oh, very good. So E1 tilde is just two E1s and one E2. And E2, that's more complicated. E2, how much E1? Well, it's 1, 2, 3 out of 1, 2, 3, 4, 5, 6. So it's half. So this is 1/2 of E1. And this looks like 1 or 2. Difficult, maybe 1.5 out of 6. Let's say it's 1 out of 6 or 2 out of 6. Either 1/6 or 1/3 of E2.
So it looks like we need 1/2 of E1, but it's in the opposite direction, so that's actually minus 1/2. And then we need 1/4 of E2. So I'll just write those in. All right, so what we've done is we've written out the new basis vectors as linear combinations of the old basis vectors. And if I wanted to, I could write these 4 numbers into 2.
Wow, this is amazing. So this is the transformation. So F is a matrix, a transformation matrix, the forward matrix. So 2, 1 and 1/2, 1/4. So that if you give me the E1 vector, this doesn't make any sense. Isn't this improper? It should be 2, 1, because you want to multiply 2 and 1 by E1. You want to have E1, E2. Isn't this incorrect? 2 and 1/2 of this doesn't make any sense.
2 by 2 matrix called F for forward. Now you'll notice that the numbers in this matrix are not arranged in the exact same way as the numbers in the equations. The arrangement is flipped about the main diagonal. The reason for this is that in this video series, we are going to arrange basis vectors as rows that multiply matrices from the left. So if
Whoa! Why would you do that? I've never done anything haven't done anything like this since the first time I saw what a matrix is. I know it's possible to do. So E1, so you multiply row by column, and that gives you the E1 tilde. And then row by column gives you E2 tilde. Fantastic. Look, as long as everything makes sense, I'm happy. I'm not going to complain.
If you remember matrix multiplication, you'll notice that this row times this column gives first entry times first entry plus second entry times second entry. And this results in our first equation for E1 tilde.
Fantastic. As long as you're not skipping steps, I'm happy. I'm a happy camper.
Applying the same procedure for this row times the other column gives our second equation for E2 tilde. So for this series, keep in mind that when we write equations to change basis in matrix form, basis vectors are written in a row multiplied from the left. And that means that the numbers in the forward matrix are flipped about the diagonal compared to the equations.
No problem.
And so that's really it. That's the entire forward transformation.
Now he's going to do the backward. So the backward, you have to solve for E1 in terms of tilde and E2 in terms of tilde. So you need to solve it. So let's say you would add these two and add these two and add these two and get E1 plus E2 tilde. I don't know. Let's see what he does.
If we know the matrix F, then we know everything we need to construct the new basis from the old basis. Okay, so what about backward transformations? As you'd expect, it's basically just the same thing, but in reverse.
Right, so you could look at this. Until now, we looked at the tilde and we mapped it. We looked at the red and we mapped it from the blue. Now let's look at the blue and map it from the red. So let's say E1. What is E1 in terms of the other guys? So, I mean, how do you project it? Like, I think you need to project it to here. So it's about 1/4 of E1. Maybe even less. It's 1/4 of E1 tilde. And in terms of E2 tilde, it's about 1 E2 tilde. Let's see what he says.
So we build the old basis vectors using the new basis vectors.
Very good. As long as he's not skipping steps, I'm happy.
We build E1 using E1 tilde and E2 tilde. It's a little more confusing this time, but it looks like we need 1/4 of E1
Yeah, that's what I thought. 1/4 and 1 of... Yeah, it's exactly what I
tilde
said.
and exactly 1 of E2 tilde. But
That's exactly what I thought. Hey, I'm getting the hang of this.
facing the opposite direction, so it's actually -1. So I'll just write those in. And what about E2?
So E2, again, we need about 1/2. It looks like 1/2 of E1. And about, it's off screen, about 2 E2 tilde.
it looks like we need a half of E1 tilde plus 2 E2 tildes. And again, we can store these numbers.
Oh, hey, this is great. That's not so hard.
In a 2x2 matrix called B for backward. And that's the backward.
Okay, let's check that this is correct. So we take these. Don't we take these? 1/4 and 1/2. Let's see. So now we're going to take the E1, E2 tilde, put it on the left, multiplied by B. So it's 1/4. Right. So it's 1/4 minus 1 and 1/2 plus 2. Correct. Yes, this is correct.
Transformation. So if we know the matrix B, we know everything we need to construct the old basis from the new basis. Now you might be thinking, here we have the matrix F and here we have the matrix B. Are these really two different things? They kind of do the same job, but in opposite directions. So are they really so different? Well, let's see what happens when we multiply them. So this might actually be a good exercise for you.
Wow. Oh my God. Are they really is there like an inverse relationship that you can map? Holy shit. No way. I don't believe it. So you do row by column. So 2 by 1/4 is 1/2. And this is 1/2. And this is minus minus. So it's plus 1/2. So this is 1/2 plus 1/2. This is 1. So this row by this column is 1. And minus 1/2 times minus 1/2 is negative 1/4. And 1/4 of 2 is 1/2. So negative 1/4 plus 1/2 is 1/4. So what does that mean? I don't know. What are we trying to do? What do we want to get?
To review matrix multiplication, to multiply two matrices, we write them like this, and to get this entry of the resulting matrix, we take the inner product of this row and this column. So in
Right, so it's row by column. Oh, row by column gives you this thing. Okay. And then row by the second column. I don't remember. That's a good question. How do you, well, what's the rule for matrix multiplication? So row by column is this. Then this row by this column, by that rule, should be this. The second row by the first column, by that rule, should be this. And the second row by the second column should be this.
In this case, it's 2 times 1/4 plus negative 1/2 times negative 1. So that's just 1/2 plus 1/2, which equals 1. So I'm going to let you do the other 3 entries. But what you'll find is you get this matrix here with 1s along.
No way. No way. No way. This is like magic.
The main diagonal and 0s everywhere else. And this is, of course, the identity matrix. So what this really means is that F and B are inverses. Or another way of saying that is B equals F inverse. So why am I using 2
No way.
different letters here? Why use F and B when I could just use F and F inverse? Well, just visually, I personally find it easier to tell the difference between F and B than between F and F with a tiny little negative 1 up here. So even though B is equal to F inverse, I'm just going to keep writing B. Okay, so that was an example in 2 dimensions.
Amazing.
What if we want to generalize this to n dimensions? Well, it's basically the same process. We have n old basis vectors, E1, E2, all the way up to En, and we have n new basis vectors, E1 tilde, E2 tilde, all the way up until En tilde. And we need to decide how to build these new basis vectors out of the old basis vectors. And we do that just by choosing the right coefficients, so that all of these linear combinations work out properly. And again, we can write these coefficients in a matrix. This time it would be an n by n matrix instead of a 2 by 2 matrix.
Okay, let's see. So F11 is the forward component of E1 and F21. Okay, and you write it here. And Fn1. And it's a square. It's n by n. Because there's n dimensions and n dimensions. Okay.
And that's our matrix F. Now, writing out all these equations is kind of annoying. So let's see if we can find a better way to write this. So if I wanted to build the EI tilde vector out of the EJ vectors, what I would want to do is write EI tilde as some sort of combination of the EJ basis vectors. but I still need to decide on the coefficient.
So you're writing this. So any I tilde is the sum over J, I think N, of EJ times F. Well, you want to say IJ, but you can't use I, and J is N. What is J? I don't know. Okay, let's see what.
So what would these be? Well, if you look up here, you'll see that F12 tells us how much of E1 makes up E2 tilde. And over here, F.
Okay, so 1 and 1, N and N. So it's J. So it's Fj X.
Fn1 tells us how much of En is inside E1 tilde. So really, the coefficient I want here is Fji. Fji tells us how much of Ej makes up.
Oh, very good. I. Okay.
Up Ei tilde. So really, this summation summarizes all of the above equations nice and simply. So this is the forward transformation in n dimensions. Now, for the backward transformations, I can do the same thing. We just write out all the old basis vectors as linear combinations of the new basis vectors. And we can write these coefficients in an n by n matrix called B. And we can summarize all these equations where Ei is equal to the sum of Ej tildes, with the coefficients being Bji. So that's the backward transformation in n dimensions. It's worth noting that with these summation formulas, we're free to relabel the summation index letters without changing the meaning of the formula, as long as we relabel the index letters consistently. For example, I can replace the summation index j with the summation index q, and the formula's meaning stays the same. We're also able to flip the order of the factors in the summation, since these are just numerical coefficients.
Fascinating. Absolutely fascinating. It's just it's a mechanical explanation. Mathematics is very mechanical, which is good.
As long as we relabel the index letters consistently. For example, I can replace the summation index.
Wait, what is he saying?
And simply. So this is the forward transformation in n dimensions. Now for the backward transformations, I can do the same thing. We just write out all the old basis vectors as linear combinations of the new basis vectors. And we can write these coefficients in an n by n matrix called B. And we can summarize all these equations where Ei is equal to the sum of Ej tildes, with the coefficients being Bji. So that's the backward transformation in n dimensions. It's worth noting that with these summation formulas, we're free to relabel the summation index letters without changing the meaning of the formula.
Right, he relabeled something. J equals 1 to n, Ji, J, 1, 2.
As long as we relabel the index letters consistently.
Oh, he's just writing it out. Okay. Oh, it could be Q. Of course, it doesn't matter.
For example, I can replace the summation index j with the summation index q, and the formula's meaning stays the same. We're also able to flip the order of the factors in the summation, since these are just numerical coefficients, and it
very good, yeah.
doesn't matter if we put the numbers in front or in behind. Okay, so we have the forward and backward transformations. Now, can we prove once again that they are inverses? Well, I'll start with the backward transformation just here, and if you'll notice, the forward transformation gives us an equation for Ej tilde. So I'm just going to substitute that in for Ej tilde here, and we.
Okay, this is the backwards transformation. From the tilde we get the original. Right, this is the back, and this is the forward. So back times the forward, right? This is the forward. This is the substitution. And he doesn't want to use, right? He can't use J here, so he replaces J with K. And this J right? Because the back is this. So he's taking this, but he wants this, he wants to substitute that. So this goes in here. But this thing needs to be summed. over K. Oh, so he already expressed this in K and this in J, but this J is this J. Wow, what a mess. Jesus. That's the problem with math. I mean, it's difficult to follow the instructions. So you're just summarizing over all the J's, and this is any one J. So you could just plug that in, and this is still correct. So you can plug this in perfectly. So he took this, he rewrote it here. There's nothing new. But now he's saying this red, well, let's take this and plug that in. As it is, it's correct. The notations are correct, but you need to summarize over J and K. So J is here and K is here. So this is double summation. Okay.
We get this. And rearranging some of the summation signs.
Okay, so he's rearranging the summation. So this is KJE. He took the summation out, and this summation he put in. So this is summation. I think we learned this when we learn sequences in calculus. Like in the beginning of calculus, we learn about series. That's the first step of calculus. Oh my God. So we learn to do series, and that's when we learn to do this. So you can switch these two and everything still holds. So you're doing this and you're still summarizing also over K. Now this you're allowed to put outside. I guess you're allowed to do all that. So this is FKJ and BJI. So I guess you're allowed to do all these things. I'm assuming this is allowed. I'm assuming someone has proved it. It just takes time and like solving problems to remember the rules.
What's up, Mr. Slave?
Hey, what's up?
I'm in the dungeon. I'm in the Discord dungeon.
What does that mean?
I was on a naughty server, and I have been disciplined by Discord.
Wait, what do you mean? What is a dungeon?
Basically, my account is in suspension status. I'm in the very limited status, which is 2 steps below my account being nuked.
Wow.
Just because I was on a server that I wasn't even paying attention to, so I don't even know what they were doing over there. I mean, it's nothing with Nazis, but I don't know.
Oh, you were
Mr. Slave. Mr. Slave, how did you find yourself here?
C-Line invited me.
Invited you?
Yeah.
Mm-hmm.
Oh, okay. How long ago?
Like a week ago almost.
Yeah,
Interesting. What a coincidence that we have ran into each other yet again in yet another community.
Wait, how do I know you?
You know Mandindin?
You're Mandible?
Yeah.
Awesome. Why are we not friends?
Mr. Prime. You know you must watch for most of the listeners. The ones who only use text chat and are in VC all the time, listening. What did I just join to, man? What's up, Mod 1? How you doing, bro?
Somebody's audio is terrible. I cannot hear you.
I said, what's up, C?
Your audio.
I'm in the dungeon. I went on a naughty. I went
This guy
on
using naughty words.
They used a lot of naughty words, a lot of naughty images.
The very most bigly fucks you won't.
Wait.
you couldn't believe.
Let me understand, C-Line. So if I go to a server where they say bad things, they nuke my account?
Yes, that is possible. I don't know
Yeah,
if this.
maybe they will nuke your account. Yeah.
Oh shoot.
Wait, Mr. Slave, you a flat earther?
No. And
He's a dumb.
Shame. That's a shame, man. The Earth's fucking measurable flat. Man.
But I am.
He's a dominatrix, though.
But I believe in the ether, so I'm an ether.
So you're a conspiracy theorist. I got it. Yeah, it's common like knowledge that if a Discord server gets banned, you have a high possibility of getting banned with it. For the simple reason that if you're on a server which is doing bad things, you're most likely also doing bad things and deserve to get your account banned.
So I should remove
Makes
myself
quite a lot of
from
sense.
most servers. You're saying if I
I
don't.
mean, are you a questionable person? Like, have you been breaking
Yeah,
the
like
law?
you know who's not questionable? I mean, is questionable. It's this
Are you
guy.
advocating? Are you saying that's like a good thing? That's like that's like a good action of
When people
moderation
don't
on
have
Discord?
real names, they're very questionable. Like
It is a good thing. It
I
is
mean,
a
bro,
good
you
thing.
realize there's plenty of servers that'll get super popular for all sorts of various communities, and then they'll get bought out by people with like nefarious intentions, and then they'll do nefarious things on those Discord. People are on those Discords from years ago. They don't even realize they're still on it. They don't realize it's changed, and they get banned.
Not everyone gets nuked. Not
Yeah,
everyone gets
but
their
a
account
lot
banned.
of people do though. So
Okay, and you have to take certain measures to ensure safety and ensure the fact that your company doesn't get sued by by
I get
people
that. I
who
get that.
have
I
the
get that.
capability.
All I'm saying is that like you tried to kind of like make the insinuation that when there's smoke, there's fire, and that's definitely not the case. There's plenty of innocent people who've gotten their account banned. Plenty.
Like me, I never posted any Nazi shit. So.
Wait, are you on a new account?
No, this account is in very limited status. I'm in the dungeon right now, and I may not.
Did you get like an email or some shit, or what is it?
Yeah, I just got a message this morning. I was in Earth Awakenings trolling the text chat, and I couldn't send messages, and then I saw that my account was locked down.
Locked
So-
down? I've never seen that before.
So you saw that your account was blocked down. Had you seen this proposed Nazi shit in this server?
What in Nord in that Nord guy's server? Are you talking about what was it North Awakenings? Northern Awakenings. Are you talking about this guy?
Many people stop being mods at servers when the other mods failed everybody, and they're going to be at risk of losing something.
Yeah, of course.
Are
My
you-
question is, are you referring to the Northern Awakenings guy's server getting banned?
Not the Northern Rebellion. I don't like keep saying Northern Awakening.
Rebellion. I don't know, like
Yeah.
I'm not big in this community. Man, he deserve to get banned. He had all these fucking Nazi worshippers there, and all these people who denied the Holocaust and all this other bullshit. I fully support it. That's about it.
Why?
Because those people don't deserve a platform.
But they're on their own little like independent platform.
I
It's
don't
like
care. I support a dictatorship.
Okay.
I
well,
think
why is that?
it's very dangerous to silence people because you're pushing them into their own echo chamber and you're exacerbating the problem.
Flat Earth. Flat Earth.
So I mean, have you ever actually? Can you give me an example of when a dictatorship has worked in history?
Russia, North Korea,
Oh, really? So North Korea, it's working.
China.
It's like actively working.
China.
The citizens are happy in
Qing
the
Empire.
economy. Oh, the
Qing
Chinese
Empire.
economy is working out perfectly fine. You're saying?
Shut up, bro. You don't know shit about economy.
You're a fucking idiot. You're just a stupid ass liberal.
Okay,
doesn't know
mute
shit.
me,
You
go
debate
off.
people on Discord when
Mute
you
me,
don't
go
actually know fucking anything about anything.
Excuse me, I live in
I love
Russia.
I love dumbass
I'm
liberal
Russian.
Europe.
I'm Russian.
Dumb
I'm the last
European
thing from
liberals. Dumbass
liberal.
European
I'm the
liberals who
last thing
don't
from
know
liberal.
anything. They wanna be fucking political. They want to fucking do political debates when they literally don't know jack shit. Hey, dude,
Okay.
I'm not
Explain
a
to
flat
me
earther.
Marxism,
Wait,
socialism
I'm not a
theory.
flat earther.
What is
Wait, wait, wait,
what
wait,
is
wait, wait, wait,
socialism in Marxist
wait.
point of view?
Let's do
What
let's
is
do
the
what
socialist
let's do what
Marxist
let's
point
do
of
what
view?
let's do what this
You just keep
Discord is
stuttering.
about. It's
Don't
about
answer. You don't answer my question.
wait, I'm
You want
asking you a
to?
question. So
Um.
Guys,
you're
guys,
gonna
guys, guys,
let's
stop, stop.
go.
Okay, you
Wait,
want me to
so
mod? You want me to mod?
Shut
you're a
up, bro.
mod.
No,
Shut up.
no. I
Wait,
mean,
wait,
you're
I'm
not
just
Shut
talking.
up.
You're making no.
Shut up.
Wait,
Shut up.
Alexei.
Okay,
Shut up, Mr. Slave.
so this is a
Mr.
Globe
Slave.
Gangsters Discord, right? I'm not a flat earther, but I'm gonna sit here and debate you on flat Earth, and I'm gonna destroy you on it because
We're
you're
not
an
talking about
idiot.
flat Earth.
So,
We're not talking about flat Earth. I'm not talking about flat Earth with
anyways, so what is your evidence of that we're living on a globe, that there's curvature to the Earth? What's your
what
evidence?
is
Can you
the
provide me
what?
some
Is, my first question was what is Marxist socialism?
Oh no, I'm not gonna do this Destiny liberal thing where you come up with
Oh.
some rhetorical question and repeat it over and over again because you don't have any actually have a point that you're trying to make.
Go away, man.
But
Go away. Go.
what you keep trying to do is you keep saying flat earther to try to like make a point, but so I'm
Flat
so
earther.
so I'm not a flat earther, but let's just go ahead and debate flat earth so I can prove to you that you don't actually have a you can't even you actually can't even make fun of flat earth.
Wait, but you guys, why don't you guys go? Why don't you guys go debate like somewhere else? Because we want to have.
Man, this guy's got his panties in a twist, man. He got sand up his ass crack.
Okay, okay. Look,
you said some stupid
He's
shit and
itching
stuff.
for an argument. He's
Alexei.
itching
You
for
said
an
some
argument.
stupid shit,
Okay.
and you can't defend your position.
Wait,
You
guys,
said-
come on.
I
You're like you're taking over the
I asked
server.
you to defend your
I
position.
know I hurt your feelings, kid, man, but I hope you have
asked
a
you to
mum to
defend
cry
your-
to. I
no,
hope
I-
you have a girlfriend to cry to. You know, I'm not
so-
your therapist.
so-
You know, I
Okay.
don't give a fuck.
So
I don't give a fuck.
calm down.
Mandibles,
Let it out.
Mandibles, can I
Let it
talk
out.
to you? Mandibles, can I talk to
Yeah,
you?
sure.
So after our previous debate, I couldn't sleep all night. And
Oh, that's a fake laugh, by the way. That's a fake European liberal.
Mandibles,
It's a
just
damage
ignore-
control. You're trying to
him.
prove that you're laughing because it's like a sort of damage control because you know you just got.
No, because I like rage bait. I rage bait Fluff.
Mandibles,
quite
just
often.
ignore him.
Right. Okay. Yeah. Sure you do. No, you don't.
Professional
Well,
rage
that's
bait.
why you
Professional
spend.
rage.
You know,
Professional rage bait.
people who don't believe in ideologies tend to spend all their time around communities regarding those ideologies.
Mandibles.
rage bait?
Okay,
What is
Mandibles,
rage bait?
Mandibles, do you want to talk to me?
Mandibles,
I gotta
what is
go.
rage bait?
Otherwise, I'm
I
leaving.
actually do want to talk to you since this guy doesn't really
So
want to
let's
engage
talk
with me.
because he's wasting our time. So anyway, after our
I am.
last, our
Mr.
last,
Slave, you're a little bit smarter than this idiot.
after our
Just a little bit,
last,
though, not a lot.
ignore him. Just ignore him. So after our last debate, I couldn't sleep all night because you brought up the weirdness of quantum physics, and you know that was for me. I've had enough of the quantum weirdness, so I decided to take a deep plunge. Alexei, could you mute your mic? You're breathing in, and we can hear all the noise. So
Oh, sorry.
thanks. So, oh, you're doing that on purpose. Anyway, thanks. So I decided to redefine science to be completely mechanical, so that you cannot introduce, no one can ever again introduce quantum weirdness into science, in my science. And then I started studying physics like crazy. And based on this new mechanical definition of science, I immediately developed an ether-based theory of gravity that also gave me a mechanical explanation of special relativity, and also a wave mechanics of quantum physics. So, thank you. You debating.
Thank you for your monologue. What is the new definition of science?
My definition of science is that a scientific theory must be 100% mechanical. So
It must be mechanical.
yes,
But a theory is only a theory until it is proven or disproven.
What?
Define mechanical.
Mechanical is causal, intuitive, simple.
So chemistry which is not mechanical, it's not physics, it's not a science.
But
Psychology,
why
which is
not?
not mechanical, is not a science.
Wait.
Art, okay,
One at a time.
not the art, but
One at a
No,
time.
no. Let me explain it to you. So by mechanical, what he means is like one thing follows another. Is
Right.
what that means. Essentially, things are deterministic. So
Right.
everything is a mechanical process. Even if it's massively emergent, there's a lot of different,
so everything
like
is science.
independent
If
variables
everything's
going
a
into.
mechanical, if everything is a mechanical process and science has to be mechanical, everything is science. By your definition.
Well,
Let's use the right words for the right epistemology. Thank you very much.
Well, the way you phrased it, I don't know if I'd agree with it. So my assumption is that the universe is mechanical. Therefore, my definition of science is that a scientific theory must be mechanical
What constitutes a scientific theory?
if it's mechanical.
But what makes a theory? It doesn't matter if it's mechanical or not.
Well, it has to be.
Is it the theory of relativity mechanical?
No. So
why is it not?
Special
very mechanical.
No. So
well, your friend here says it's not at all.
right. So special relativity postulates the speed of light to be a constant. A postulate is not a mechanical explanation. There's no mechanical theory that proves that the speed of light is a constant. There's no mechanism by which, therefore, the speed of light is a constant. Rather, it's postulated that, given that the speed of light is a constant, let's derive all sorts of phenomenon. That's not a scientific theory. The same goes.
Well, arguably, we have measured the speed of light. It is constant. It doesn't change.
Yes, but that is a postulate.
People have gotten different measurements.
Yeah, but that's a postulate. That's
you have plus minus. You have room for error. You must also always account this in any experiment. You must always account room for error,
Yeah,
whether
of
it's in
course.
mass, in
Of course, I get it.
moles, in time,
get it,
whatever
I
it
get
is, in joules, temperature, whatever. It doesn't matter.
Right, but you you never presented a mechanical explanation for why the speed of light is a constant.
So but this is the thing, Slave. There's absolutely zero theories of everything that have zero postulates. So every single one has some sort of hidden variables that you have to assume. I mean, and you just said that you believe in an ether. You're postulating an ether. What mechanical theory do you have to prove the ether?
Right. So you're right that I am postulating, but I'm providing a mechanic. Well, I'm postulating the ether, and based on that, Alexei, please mute your mic if you don't mind. So, based on the assumption of the ether, I can mechanically derive the constancy of the speed of light. Based on the postulate of the ether, I can mechanically derive the law of Newtonian gravitation and general relativity.
Newtonian gravitation describes light as mechanical.
But
As
you're
light is considered a wave that propagates at a constant speed in a vacuum.
Well, that's actually
This has been proven
Maxwell's.
by the Danish astronomer Olaf Romer. It's been proved many, many times by measuring the eclipses of Jupiter's moon, of distances from the Earth. He notes the farther you are away from Jupiter, the time between the eclipses increases, and this is only explained by the constant speed of light. There's also other explanations as to why light's mechanical, but that's long.
I mean,
it can move at different speeds.
But the question, the fact that you observe something, that's not a theory, that's an observation. A theory is the attempt to explain an observation. So no one has ever tried to give a mechanical explanation for the observation that the speed of light seems to be a constant.
What about the fact
listen,
that
dude,
it oscillates and tickles surrounding atoms?
What?
This generates magnetic waves or electromagnetic waves, and
there is no
electrons.
No one has ever attempted to explain mechanically why the speed of light is a constant. Everyone has always just accepted.
You must have not searched the web well enough.
If there was a theory that mechanically explained like every single hidden variable, then science would, and it was unfalsifiably proven, then I mean science would be over. Like physics would literally be solved. You know what I mean?
So you don't
we
believe
don't
in
have a
science.
mechanical.
You believe the Earth's flat.
We don't have a mechanical theory of everything. So no, dude, this isn't coming from a conspiracy perspective. Physicists will agree on you. Nobody actually thinks that the theory of relativity is like fundamental reality. But
theory-
besides dumbasses who watch Neil deGrasse Tyson and like think that, you know, like Rick and Morty watchers and stuff like that.
And dumbasses who watch Neil deGrasse Tyson still thinks the Earth's flat.
The
I
theory.
think the Earth is flat, dude. I just said I'd own you on a debate in it because I know you're a bad debater, but that's all right.
The theory of relativity is not a theory because, according to my definition, it doesn't provide a mechanical explanation for the constancy of the speed of light, and it does not
Let's just
provide.
talk about your definition, man. Give
Bro,
me your dictionary. How about you give me your
what is your-
dictionary? You have so many
what is-
definitions. Give me your fucking
What is
dictionary. at this point.
what is your mechanical explanation for the existence of the ether then? You can derive things from it, fine, but you already postulated its existence, so that you have to give the mechanical explanation for the existence of it too.
No, I don't. So I'm allowed. So my definition of science is that a proper scientific theory peels one layer of the unknown proverbial onion at a time. So I don't have to explain the universe completely. All I need to do is peel one layer of the unknown. So right now
You're putting that burden upon the theory of relativity. You're saying they have to prove the constant of light. You know, I'm not too educated on, you know, the constant of the speed of light and how they've derived mechanically why it is what it is or
They
whatever. I'm
didn't.
sure it's just one of those variables.
It's a
Right, but
postulate.
they didn't. Sure, it's a postulated, but why do you not need a burden to prove the existence of something and they do? Like they are actively trying to prove that. They're trying to figure out why these variables of the universe are the way they are like, you know, what do they call it? The whatever. They're trying to figure out why the variables are the way they are, why the constant is what it is. And so if you're trying to do that with the ether and you're trying to peel back layers, why can't they do that too? Because they've peeled back more layers than you have with your ether.
Right. So by my definition of science, the theory of relativity is just not scientific because it doesn't provide any mechanical explanation for what it is describing. It is just
You're just repeating yourself though. Like we get it, but you're not providing any mechanical explanation for what you're describing, and everything is derived from the ether, literally everything, and you're not giving a mechanical explanation for it. So
But I am giving a mechanical explanation for two things. For the Alexei, I think you're making noise. So I am providing a mechanical explanation for the constancy of the speed of light and for the phenomenon of gravity. As I said, I'm revealing one layer of the unknown. Einstein didn't reveal anything about the universe. He just postulated a constant speed of light. There's no.
yeah, and it just works, right? We get it, like just works. And I don't necessarily think that the theory of relativity is true at all. I think that it's probably off. It just works better, you know, for the physics. But also we have falsified the ether. That's the problem.
Okay, so the ether, as far as I'm concerned, has been validated, not falsified, because the theory of special relativity predicts that Michelson and
hold on.
Morley.
Sorry to interrupt. Peter, are you there?
Who's Peter?
Oh no, he dropped.
Hmm.
Okay, never mind.
So.
Hello?
Yeah, we're
Peter,
here.
I'm in the dungeon.
You're where?
I'm in the Discord dungeon.
What does that mean?
It means that my account might be getting deleted.
Why?
And because I was on Northern Rebellion's Nazi server, and I didn't realize they were constantly posting Nazi shit because I joined it and then forgot about it.
And what, like Discord nukes your account if you hung out with the Nazis a little bit?
Yeah.
Oh
I
my
didn't
god.
even over there. I didn't even have like any. I wasn't even a moderator.
Did they send you some kind of like official communications?
They just sent me no. All I got was a message from their bot saying that my account was flagged for TOS because I was on a violent extremism server.
Wait,
Yeah, but that's probably because, you know, the bot just looks at all the members and sends them this note, right? When they're shutting down the server, but sure you can appeal it or something. There's no way that they can be this crude in their enforcement of TOS.
I don't know, man. Apparently they've this is Jesse's account was nuked, but he was a moderator. But
Jesse's account got muted.
Anyway, let's see what this guy is saying. Well, 30 doesn't revolve around what you think, little bro. What? Mandible is actually a good guy to talk to. Very good. I don't know. He's okay. He's an okay guy. I don't know. I don't know if I enjoy talking to him so much. All right, let's see. So we were here. So I need to learn how to play with summations. I remember that you can do anything with summations. You can move back, forth, anything. Because I mean, the J talks about the JI. So here is the J and here is the JI. So you're still summing over the JI. And summing over the K, right? So you're summing over the K guys. And this is summing over the K and this is summing over the K. So you're still summing over everything. So nothing has changed. And summing over, right? These three are being multiplied. Factored? I think multiplied. So, but we still need to prove this. We'll be back. I mean, I'll get back to learning how much of a leeway you have in this game. Anyway, so he's playing around with this, and he's got this. And now J, K, J, J, I is this is FB. Oh, but we know FB is 1. Oh, is this 1? So this is just K. So EI, is it just E? Does this cancel itself out? Let's see what he says.
Science, we get this. Okay, so let's just put this on a new slide here. So looking at the formula, what's going on here is that we're building the old basis vectors using a summation of the old basis vectors. And
Old from old. Oh my god. So this must be 1. I mean, that means this must be EI.
Need to do is we need to decide what this middle part of the equation should be. So why don't you pause the video?
It can't be just 1 because you're still summing over the K's. And the K, I think, is up to N. This is, I don't know if we proved that F times B is 1. I don't know. I need to stop the video and think about it. I can't imagine what's going on. I mean, the nice thing would be if we could write this out. just write it out. For all the J's, this is just for the J's. For all the J's and all the K's, but for a single I. So this is just for one of the I's. So this is the back matrix. This is the forward. Let's see what he says.
And take a few seconds to think about what the middle part should be, if we want these equations to make sense. Okay, so what we really want at the end of the day is for E1 to equal E1, and we want E2 to equal E2, and so on and so forth. We don't want any extra basis vectors in here being added, because that wouldn't make any sense.
Yeah.
So what we really want is for this middle part to be 1 when I is equal to K, and we want it to be 0 when I is not equal to K, right? That makes sense.
Okay. Oh, and I equals K, so this is the identity matrix. So when I is equal to K, then it's only one term that is I.
And really, if you think about this as a matrix, where I gives you the row and K gives you the column, putting 1 where I equals K means having 1s where the row is equal to the column. So we get 1s along the main diagonal here, and then we just get 0s everywhere else. So again, 1s along the diagonal and 0s everywhere else. Once again, we showed that multiplying F by B gives us the identity matrix. So F and B are inverses of each other. Now, this behavior where we have 1 where I equals K and 0 where I does not equal K, this behavior ends up being so common that we give it its own symbol, called the Kronecker delta. So whenever you see—
Wow. This is so incredible. This is like a puzzle that all the pieces make sense.
the Kronecker delta, just think of this relationship right here. It's
Wow, this is Kronecker delta that IK, if they're equal, it's 1. And that's incredible. That's this delta. That's this claim. Wow.
It's a bit like telling you what the entries of the identity matrix are, where we have 1 where the row is equal to the column and 0 everywhere else. Okay, so to sum up what we learned in this video, we learned the formulas for the forward and backward transformations in n dimensions, and we also showed that the forward and backward transformations are inverses of each other, because when we multiply the F and B matrices, we get the identity matrix.
But what about B times F? We didn't prove that.
Whose entries are given by the Kronecker delta symbol here.
Oh, so it's equal to Kronecker delta. That's the identity matrix. Wow, but this is not a matrix notation. This is just a value. Wow, this is incredible.
In the next video, we're going to look at vector components, which allow us to build generic vectors out of basis vectors, where the components are normally written as columns. The forward and backward matrices will transform the columns like this.
Okay, so V1, V2 tilde is the back matrix times the original V, and V is the forward times the tilde. So you start, isn't this the opposite? Isn't this forward? Don't you go to 2 tilde? You start from V. Why is he saying backwards? Isn't this the reverse? So V is V1. This is nice, okay. But this is a vector. This is the backward transformation. So this is the E times the V, because he wants to put the vector, the basis, in front of the components. Wow. Everything is backwards in tensors. Unbelievable. Okay, so what I want to,
Welcome back to the video series on tensors.
Okay, we'll come back to this. I want to take a look at if anyone teaches just summation. Let's just look at summation. Oh, roundup.
Destroy tunnels. And he's saying, you probably can't take it out, Israel. Maybe the United States could. Maybe, but why not? Let's be optimistic. Mexico's president already. Fundamental principle. Everybody's having a fantastic day. I have a feeling that these are going to be a permanent part of the show. They have been for the last year, pretty much. We'll talk about FEMA and we're having a fantastic Friday and looking forward to your weekend. All right, we're gonna jump in today with another Middle East update. I have a feeling that these are going to be a permanent part of the show. They have been for the last year, pretty much. We'll talk about FEMA and disaster relief. Jobs report out today. Mexico's president already creating conflict, and we'll talk about reading books. People don't like to anymore, so we'll talk about that. Let's see. So we've already started with the super chat. Thank you, Hunter, Remo, and Michael Sanders. So we're off to a crazy start on the super chat. I appreciate that. Keep it coming, people. Also, Ryan Ward suggested maybe today should be a good day for $1 sticker Friday. $1 sticker Friday. That means anybody who doesn't want to ask a question, just do a $1 sticker. Ryan did $1.49 Canadian, which is about $1 American. So a $1 sticker Friday. Maybe we'll turn it into tradition, and then one day in the future, we'll call it, I don't know, $10 sticker Friday or $100 sticker Friday. We'll just get more ambitious over time. But yeah, $1 sticker Friday. What attendances we had the last few days? $1 from everybody. Justin went crazy here. Thanks, Justin. Thank you. But why not? Let's be optimistic. And some of the most significant attacks they've launched over the last year since the Houthis have been states, and I guess the United Kingdom launched attacks on the Houthis. Why not? Let's be optimistic and pretend it might be true. Today, the United States and I guess the United Kingdom launched attacks on the Houthis in Yemen. Some of the most significant attacks they've launched over the last year since the Houthis have been obstructing the shipping lanes out of towards the Suez Canal. 15 different targets were hit. There was at some point a rumor that they were trying to kill the leader of the Houthis. Now that would really be inspiration for the Biden administration to actually go after a head of the Houthis. I don't believe they're doing that. That would be way too good of them, but probably not in the playbook. So yeah, the U.S. is hitting the Houthis hard. I mean, not very hard. Let's be serious. I mean, if 15 attacks, if you consider the number of planes that the U.S. has in the region, the number of ships, the number of assets, just the number of military capabilities that the U.S. has in the region right now. I mean, they could be pounding them in hundreds, and they could do it every day, and they could basically shut down the Houthis completely within a couple of weeks, destroy the capabilities to wage war, and maybe invite the Saudis to invade and destroy them once and for all. But that would be way beyond. That would be going beyond the call of whatever. Let's see, John Parker, thank you. DF, thank you. Jesper came in with another $3. Thank you, Jesper. So yes, a $1 Friday, $1 sticker Friday seems to be taking off. So keep it going, guys. This is great. So that is the Houthis. My sense is Israel did more damage to the Houthis in one short attack than the United States has done in 15 today. But they seem to have increased the intensity over the previous few days. So we'll give them credit for that. And all right, let's see. So that is
Wait, what?
one short attack than the United States. Friday, $1 sticker Friday seems to be taking off. So keep it going, guys. This is great. So that is the Houthis. My sense is Israel did more damage to the Houthis in one short attack than the United States has done in 15 today. But they seem to have increased the intensity over the previous few days. So we'll give them credit for that. And
What does it mean 15? What are these numbers? 15 what?
And all right, let's see. So that is the Houthis. Let's see. What did I want to cover in terms of Israel? So Israel yesterday, we talked about during the show, major attack on a Hezbollah bunker in Beirut. Again, something like 80 bombs in one location, huge crater. It does indeed look like they were going after the new head of Hezbollah, the guy who replaced Nasrallah, Salahuddin, and by all indications they got him. It's not clear that he's dead, but at least it seems like he is, and indications are that he is, together with a number of other high-ranking Hezbollah officers, as well as Iranian Islamic whatever Revolutionary Guard people are also among the casualties. So yes, Israel continues to assassinate leaders within Hezbollah. Assassinated yesterday also. They managed to kill the head of communications for the Hezbollah movement. Now I was wondering, how are there so many people to kill? Didn't the beeper attack take them all out? Well, here's a good example. This guy had a beeper. He had his basically hand blown off. He's without a hand, but he's still running communication for Hezbollah. Though, is he the guy who bought the beepers? The guy who bought the beepers. I mean, communications sounds like a beeper kind of job. So I don't know if I would keep him around after that fiasco. Anyway, he was running the beepers, and in spite of the fact that his hand was gone, he was still running the program, the communication program. And the Israelis came out yesterday because life with only one hand is basically for Hezbollah leader not worth living. So Israel made sure that he's not living. So that happened. Yesterday. Another one of Hezbollah's leaders taken out. By the way, yesterday, what is going on here? With the new M4s, my computer's giving me a little bit of a. Yeah, we need Apple needs to come out with the new M4s. Really needs to come out with the new M4s. All right. Yes, Israel is slowly decimating Hezbollah senior ranks. They are also doing what they can to kill junior participants. So by some estimates, the Israeli limited incursion into South Lebanon has already killed over 250 Hezbollah fighters. The infrastructure that they built along the Israeli border is slowly being dismantled. But dismantled sound too civilized, blown up, incinerated, destroyed. Yesterday, 2 Israeli soldiers were killed in the Golan Heights from a drone attack from the Iraqi Shiite militias. So they launched a drone attack against Israel, and 2 Israeli soldiers were killed. I have a feeling that the Iraqi militias, who to date are kind of only used to kind of having to deal with with American reprisals or American responses to their initiations of force, maybe are now going to feel what it's like for somebody real like the Israelis to actually attack them. So expect, if you're in Iraq, if you work for one of the Iraqi militias, expect a significant attack. You remember yesterday, Biden basically communicated to the world publicly, and I guess to Israel, publicly and privately, that they should not attack the nuclear facilities. They shouldn't attack the nuclear facilities. I've got some color on that, and maybe one reason why he said that. We'll talk about that in a minute. But today he said yeah, they really shouldn't attack the oil fields either. They shouldn't attack the oil facilities either. In other words, Biden, who claims to be in constant communication with the Israelis about the strategy moving forward, hopefully, the Israelis are going to ignore the Biden administration completely when it comes to this. Is basically telling Israel, can't bomb, you shouldn't bomb nuclear facilities, shouldn't bomb the oil fields. A few bombs in the desert, just symbolic, something symbolic. It makes a lot of sense. That's what you should do. That will really reestablish deterrence and make it possible for us to maybe negotiate a deal with Iran before the elections. I don't know what these idiots are thinking, but we talked. I got angry yesterday about the appeasement of the Biden administration, how awful it is. Anyway, two relevant stories about not attacking the nuclear facilities. One, you hear a lot about this idea that Iran could, get enough uranium within a couple of weeks to build a bomb, and that is probably true. That is, they're probably just a few weeks away once they make the decision from producing the uranium necessary for a bomb. But to actually go from that and to actually build a functioning bomb, experts estimate, and again, I don't know how good these experts are, I don't know how knowledgeable they are, but it seems like experts are estimating that something like that would take about a year of hard work to figure out how to actually put that uranium and create a bomb. Now, if the Russians help or the North Koreans help, maybe they could do it faster. But I guess the estimate now is we have about a year to stop the Iranians from building a bomb, and the Iranians have about a year to build a bomb. So that's interesting. So it's not a few weeks, maybe it's a year. But the other interesting story comes out of Israel, where a former prime minister, Ehud Barak has been prime minister, he's been secretary of defense, he's been, a military chief of staff, he's been pretty much everything, militarily head of special forces and so on. And when he was defense secretary about 15 years ago, under Ehud Olmert 20 years ago, and Bibi Netanyahu about 15 years ago, he was probably the biggest voice, the most articulate voice, the most passionate voice. Whoops, we got are we freezing? Is video okay? I'm curious. Video okay? Yeah, well, I can't see anybody on the chat. Fine, I'm told. All right. So Ehud Barak, who was an adamant supporter of attacking the Iranian nuclear facilities 15 years ago, who lobbied for this within the Israeli government and outside of it, by the way, again, a good, it was Netanyahu who blocked this, and it was the Bush administration and the Obama administration who both blocked it, but Ehud Barak was one of the advocates for attacking the nuclear facility. Anyway, Barak is now coming out and saying it's too late, which is really interesting. He's basically saying, whatever damage you do to the nuclear facilities now, it's too little, too late. You might slow down the progress, you will not stop it. That is that the Iranians are within reach of a nuclear bomb within a year, and nothing Israel does militarily can really stop it. Now, I don't know if this is true or not. I'm not an expert on these things, but Ehud Barak has no incentive to say this. Again, he is an Israeli. He's somebody who knows the Iranian nuclear program really, really, really well, has access to classified information, unlike me. And he's saying, you probably can't take it out, Israel. Maybe the United States could. He's not saying that, but maybe they could. Israel probably can't. It's just too late. Now, let's assume that's true. And it might be true. I just don't know. What should Israel do if that is true? Well, then Israel has only one path to proceed. Because, look, the one thing Israel cannot allow, and given that the United States won't do anything.
Then Israel needs to nuke Iran.
And it's clear in my view that neither Trump nor Biden or no Kamala will do anything. Then the one thing Israel can actually do, if it cannot get to the nuclear facilities themselves, it cannot retard the nuclear program itself. And again, I'm not saying that's true. I'm not convinced it's true at all, but it's certainly a possibility. Then the only alternative is regime change in Iran. And this is almost as impossible as destroying the nuclear program. How do you achieve this? Well, I mean, in my view, you achieve it by doing what has been done to Hezbollah. It's by systematically taking out the leadership of the Iranian state, assassinating Khamenei, assassinating the Council of the Guardians or whatever the hell they call themselves. Now, it might be impossible, but weakening the Iranian state as much as possible, taking out as much of their facilities that make it possible for them to retaliate and send missiles into Israel, destroying as much of the Islamic Revolutionary Guard as possible, and at the same time communicating to the Iranian opposition full support for any attempt that they make.
Okay. Oh, I wanted to look at summation. Sigma notation. This is good. But I think the Khan Academy, how many videos? Just one? And this is like part of a series? No. Like I need... So what I need is Sigma notation advanced higher math. Let's see what else we got. What I need are the rules, mathematical proof, sigma notation formula, 5 minutes. Let's see this.
Here's example 16 in mathematical proof. We've been working through a few examples on sigma notation and evaluating series using the formulae for sigma k, sigma k squared, sigma k cubed. If you haven't seen examples 14 and 15, then please go and check them out. So
This is not what I'm looking for. Like, what can I do? Oh, you know what? Double sigma notation. Let's write double sigma notation. Double sigma notation. Mm-hmm. 1 minute, 6 minutes.
our next section is going to be on double summations, and these are actually a little bit more complicated. The indexing is a little bit tricky to work with, but they do come up, and they're going to come up quite a lot inside of algorithms. So let's take a look at an example. And the example that we're going to use is going to be the sum, and we're going to be I equals 1 up to 4, and then we're going to take the sum of j equals 1 up to 3 of ij. Okay, so we're going to notice is you've got two summations, right? And so we have to actually understand what this means, all right? So we're going to work from the inside out. So much like functions, you work from inside out, so we're going to start with the inside. And unlike the single summations, where what you're doing is you're just taking the value for j each and every time, what we've got to do is we've actually got to write out, in this case, we've got a couple of summations that we're going to write out. So we're going to substitute 1 in for j, and then 2 in for j, and 3 into j. But then that means that we're going to end up with a sum, I equals 1 up to 4 of, in this case, 1i. So that's when j equals 1 plus the sum, I equals 1 up to 4 of 2i, that's for j equals 2, plus the sum, I equals 1 up to 4 for 3i. So what you're going to notice is that we're actually going to iterate this summation. We're going to iterate the outer summation as many times as we actually.
Oh, that's very interesting. So he's saying what this means, it's the same thing over and over, but each time j has a different value. So the second one but he's switching the order, confusing a little bit. So j is 1, j is 2, j is 3. So j is 1, j is 2, j is 3. And each one you're summing over the I. So this one is I equals 1 plus I equals 2 plus I equals, so it's 1 times 1, 1 times 2, 1 times 3, 1 times 4. Add them all up. And this is 2 times 1, 2 times 2, 2 times 3, 2 times 4, add them all up. And this is 3 times 1, 3 times 2, 3 times 3, 3 times 4, add them all up.
Actually have the inner summation, all right? And so now we're going to have to evaluate each one of them. I equals 1 up to 4 of I, right? It's going to be 1 plus 2 plus 3 plus 4 plus, and then now we're going to take 2 times I plus, so that's the first summation, plus 2 plus 4 plus 6 plus 8. That's the second summation. And then we have the third summation, which is going to be 3 plus 6 plus 9 plus 12.
Mm-hmm.
Okay? So you'll notice that what we've done now is we've taken that outer summation, right, with the new sequence that incorporates all of our values for j equals 60. Is to note is 3 times 10 to I. I can actually pull that. The summation of I ends up being 10. So that means that this is just going to be 2 times 10. Ta-da, and that's 20. It's kind of a cool little thing that you can do when you're working with your summations. Now let's take a look at another example.
Wait, did he
4 of 2i. I can actually pull that scalar out of the summation, and then I can make it 2 times the sum I equals 1 up to 4 of I. Now I know what the summation of I is. The summation of I ends up being 10. So that.
Oh, this is interesting. So here you could have pulled out 1, and you could have pulled out 2. You could have pulled out 3. So it's just a summation of 1 to 4. So just 1 plus 2 plus 3 plus 4 times 1. Now 1 plus 2 plus 3 times 4, well, 4 plus 3 is 7, plus 2 is 9, plus 1 is 10, right? Let's say it's 10. So it's 10 times 1 plus 10 times 2 plus 10 times 3. So it's 30, 40, 50, 60. Wow. So you could have solved it much quicker.
So that means that this is just going to be 2 times 10. Ta-da, and that's 20. It's kind of a cool little thing that you can do when you're working with your summations.
let's take a look at another example. Let's look at another example of double summation. So we're going to take the summation I equals 1 up to 3 times the summation of I equals 1 or j equals 1 up to 2 of I minus j. So again, we're going to do the inner summation first, right? Nice that there's not too many of them. And so this is going to end up equaling, right, the sum.
Well, you're going to do the outside one first. I equals 1 to 3.
I equals 1 up to 3 of.
And the inner one, well, you're going to write it out. So you're going to have the parentheses, right? So this is I minus 1 plus I minus 2 plus I, then that's it.
I minus 1 plus the sum I equals 1 up to 3 of I minus 2.
Forgot that. Oh, I was just going to put it in parentheses. Wait, this is interesting. I wasn't thinking about this. So, oh, sorry, the summation of this thing, 1, 2, 3, the summation 1, 2, 3 of 1 to 2 of this thing. So what are you actually saying here? So I was thinking it's a summation the inner one I would have parentheses. Oh, this is difficult to imagine what's going on here. Summation of j from 1 to 2. So I minus 1 plus I minus 2. Right? That's what this means. But what he's saying, did he explain this?
And these are actually a little bit more complicated. The indexing is a little bit tricky to work with, but they do come up, and they're going to come up quite a lot inside of algorithms. So let's take a look at an example. And the example that we're going to use is going to be the sum, and we're going to be.
This is 5 episodes.
Okay, so we have this double summation here. The sum between I equals 1 and 3, the sum between j equals 3 and 6 of I plus j. What's the answer? A lot of people tend to get this wrong. Okay, so let's have a look. First of all, what does it mean? Well, we can actually put a sort of bracket around here, because what it means is that first of all, we are going to do this sum, and then we're going to do the inside sum each time we iterate the red sum. So in actual fact, this double summation could be rewritten as, for I equals 1, we are going to do the sum between j equals 3 and 6 of 1 plus j, which is putting I equals to
I equals 1, I equals 3, 6. One equal 1. What is he saying here?
to 1 in there. And when I equals 2, which will be the second summation of this, I equals 2, we're going to do the sum between j equals 3 and 6 of 2 plus j. And the third iteration here will be I equals 3. We're going to do the...
So our next section is going to be on double summations.
And this one, let's take a look at evaluating a double sum. I have this double sum. So this is going to be my outer one. Say y goes from 1 up to, say, 3. And the inner one will look like this. So x goes from 1 up to 2. And imagine an expression that we want to sum up as x plus y. So how do we do this in some kind of organized way so that we get to some kind of answer?
The question is, what does this mean? What are you actually saying? Right? I would look at the interior first. So you have x plus y, and you're summing for x equals 1 to 2. So you're going to replace x equals 1 plus this thing when x equals 2. You're going to sum them up. That's what this thing means. So you can replace that. And you're going to end up with 1 plus y plus 2 plus y. That thing you're going to be summing up.
Lively. A way of doing it, not the only way, again, a way is, okay, this is step 1, step 2. Basically what I do is I'm going to grab y equals 1 first, and then I iterate over the x's. So I'm grabbing the y equals 1 first because it's coming from down here. That's the lower limit on the y variable. Let me erase that smudge. So then after that, I iterate over the x's. When I say y equals 1, that means here in the expression x plus y, you put in the following. Put in x plus 1. I'm replacing y with this value of 1. And then I iterate over the x's. So x goes from 1 up to, say, 2. When I carry this out, I'll have this form right here. So it's going to give me replace x with 1 first. You had the 1.
So he's doing the exterior first. So he's holding the interior constant. I don't understand what he's doing.
That's the value of y. Then you repeat that. You add again.
He's not explaining.
So our next section is going to be on double summations.
There it is. Change.
Let me tell you guys that the answer to this right here is... Okay, let's do some math for fun. Here I have this double summation for you guys. And whenever we have a double summation, be sure we do this part first and then that one. So first we have the sum as n goes...
This guy has 1.3 million subs. Jesus. Okay, this is the question. So changing order of double summation.
1 to n and we have 1 over 2 to the n plus n's power.
Move your hand. Okay. So sum m equals 1 to infinity over n equals 1 to m of 1 over 2 to the m plus n. What does this mean? So 2 to the m. Oh my God. So you can't just think about it separately. Can you think about the interior separately? 1 second. Who's talking? Gemzy. Oh yeah, I was talking. Anyway, I gotta go eat. I'm becoming very hungry, so I need to go eat. Must go eat. Okay, let's stop here. We'll continue after.